There's something undeniably thrilling about staring up at the night sky and realizing just how much we don't know. The universe, for all its breathtaking beauty, is a master of keeping secrets, whispering riddles in the form of cosmic phenomena that defy explanation. Think about it, even with all our advanced telescopes, supercomputers, and decades of research, there are still forces at work out there that leave scientists scratching their heads. Dark energy, an invisible pressure tearing space apart, fast radio bursts, sudden blasts of radio waves from deep space with no clear source. These aren't just curiosities, they're gaping holes in our understanding of reality itself. But here's what makes these mysteries so compelling. They're not just academic puzzles. They force us to confront how small we truly are in the grand scheme of things, while simultaneously showcasing the audacity of human curiosity. Every unexplained flash, every inexplicable pull of gravity, is a reminder that the universe still has stories to tell, stories we're only beginning to decode. And that's where the adventure begins. Today, we're diving into 45 of the most mind-bending enigmas out there, the kind that keep astrophysicists up at night. Some might hint at entirely new laws of physics. Others could rewrite the history of the cosmos. All of them challenge us to rethink what's possible. So why should you care? Because these aren't just problems for scientists in lab coats. They're clues about the fabric of existence, about where we came from and where we might be headed. Whether it's the eerie silence where extraterrestrial signals should be, or the ghostly particles passing through your body right now without a trace, these mysteries are part of your story too. This journey won't just show you the edges of our knowledge, it'll invite you to stand at the frontier, peering into the unknown alongside the researchers racing to make sense of it all. Ready to have your perspective stretched? Let's begin. Imagine if nearly a third of everything around you, the chair you're sitting on, the air you breathe, even your own body, was invisible. Not just hidden, but utterly undetectable by any instrument we've ever built. That's the maddening reality of dark matter. We know it's there because we can see its gravitational fingerprints everywhere, galaxies spinning faster than they should, light bending around empty patches of space, entire clusters of stars held together by some unseen glue. Yet after decades of searching, we still can't say what it actually is. This isn't just a case of missing a puzzle piece, it's like realizing the puzzle was never the shape we thought. Take something as simple as a spinning galaxy. Based on the visible stars and gas, the outer edges should move slower than the center, like planets farther from the sun. But observations show the opposite. Stars at the edge whip around just as fast, as if gripped by some invisible hand. The only explanation: there's 6 times more mass out there than we can see. So what could this phantom substance be? The leading guess involves hypothetical particles called WIMP, weakly interacting massive particles. These would be like cosmic ghosts, barely noticing ordinary matter except through gravity. Underground labs hunt for them using vats of liquid xenon, waiting for the faintest shudder when a WIMP bumps into an atom. But after years of silence, some scientists are exploring wilder ideas. Could dark matter be made of primordial black holes forged in the chaos of the Big Bang? Or actions, particles so light they dance through lead like it's not even there? The most unsettling possibility: dark matter might not be a thing at all, but a sign that gravity itself works differently on cosmic scales. Modified Newtonian dynamics, or MUND, suggests tweaking the laws of physics could explain galactic rotations without invisible matter. Yet even this radical idea struggles to explain all the evidence. What's astonishing is how much rides on this mystery. Dark matter's gravitational scaffolding shaped the early universe, pulling gas into the first galaxies. Without it, we might not exist, and yet it refuses to show itself. Laboratories buried under mountains, detectors bolted to the International Space Station, all sit in wait for a signal that could rewrite physics. Until then, dark matter remains the universe's most consequential game of hide and seek. If dark matter is the universe's invisible scaffolding, then dark energy is its mysterious engine, a force so baffling it makes galaxies flee from each other faster than light should allow. Picture this: the cosmos isn't just expanding, it's accelerating, as if some unseen hand is pressing harder on the gas pedal with every passing second. And here's the kicker: this dark energy makes up 68% of everything in existence. That's more than twice the influence of dark matter, and we understand it even less. Einstein briefly toyed with the idea of a cosmic repulsion he called the cosmological constant, a sort of anti-gravity woven into the fabric of space itself. He later dismissed it as his greatest blunder, but modern astronomers think he might have been onto something. Empty space, it turns out, isn't empty at all. Quantum physics suggests it's a seething foam of particles flickering in and out of existence, each birth and death releasing tiny bursts of energy. Could this be the source of dark energy? The math almost fits, except the predicted energy is a staggering 10 to the power of 120 times stronger than what we observe. That's like expecting a supernova and getting a birthday candle instead. Then there's the phantom of quintessence, a theoretical energy field that fluctuates over time, growing stronger or weaker like cosmic tides. Unlike Einstein's static constant, quintessence could change the universe's expansion rate in unpredictable ways. Some models even suggest it might one day reverse, causing space to collapse in a big crunch. But here's where things get eerie. Recent measurements of distant supernova and galaxy clusters reveal discrepancies in the expansion rate, hinting that dark energy itself might be evolving. What does this mean for the fate of everything? If dark energy keeps strengthening, it could eventually overpower all other forces in a catastrophic big rip, shredding atoms apart in the final moments of spacetime. Or perhaps the acceleration will plateau, leaving galaxies adrift in an ever colder void, their light stretched into undetectable whispers, the scariest possibility. We're witnessing the first flickers of a process that will erase all traces of the Big Bang, leaving future civilizations with no clue the universe ever had a beginning at all. The hunt for answers is as desperate as it is daring. Telescopes like the Dark Energy Survey and the upcoming Nancy Grace Roman Space Telescope map the cosmos in unprecedented detail, searching for distortions in spacetime that might reveal dark energy's true nature. Meanwhile, quantum physicists race to reconcile the impossibly large with the vanishingly small. One thing's certain: solving this mystery won't just tell us where the universe is headed, it'll force us to rewrite the laws of reality as we know them. The Milky Way isn't just drifting through space, it's being hauled, along with hundreds of thousands of other galaxies, towards something we can't fully see. Lurking behind the thick veil of stars and dust near our galaxy's center is a gravitational nightmare known as the Great Attractor, a region of space so massive it bends the motion of entire galaxy clusters toward it like a cosmic whirlpool. Imagine tossing a handful of leaves into a river and watching them all swirl toward the same unseen current. That's essentially what's happening to us, except the river is spacetime itself, and the current is a mystery we've barely begun to unravel. At first, astronomers thought this colossal tug might come from a familiar source, a supercluster of galaxies, perhaps the most massive one in our cosmic neighborhood. But when they mapped the region using infrared and radio telescopes to peer through the Milky Way's obscuring dust, the numbers didn't add up. The Great Attractor's pull was far stronger than any visible cluster could explain. It's like standing on a beach feeling an undertow, only to realize the ocean you're staring at isn't big enough to produce that kind of force. Then came the real twist. As telescopes grew more powerful, they revealed something even more unsettling. The Great Attractor itself is being pulled toward an even larger structure, a mind-bending assembly of galaxies called the Laniakea supercluster. Picture a Russian nesting doll of gravity. Our local group of galaxies is part of the Virgo supercluster, which is just a tiny suburb of Laniakea, a sprawling cosmic metropolis 500 million light-years across. And yet, even that might not be the end of the story. Some researchers suspect there's something beyond Laniakea, something so vast and dark it's reshaping the large-scale flow of the universe itself. So what's really out there? One theory points to dark flow, a controversial phenomenon where clusters of galaxies appear to move in a coordinated direction toward the distant edges of the observable universe, as if drawn by something unimaginably massive, perhaps remnants of ancient inflationary ripples from the Big Bang, or structures so far away their light hasn't had time to reach us. Others wonder if the Great Attractor is just a shadow cast by something even weirder, like a defect in the fabric of space-time left over from the universe's birth. The deeper we look, the clearer it becomes. Gravity's reach extends far beyond what our eyes or instruments can see. Every time we think we've found the source of the pull, the universe reveals another layer, another hidden hand guiding the dance of the cosmos. And that's the thrilling frustration of it all. The Great Attractor isn't just a destination. It's a signpost pointing toward mysteries we're only beginning to grasp. One moment, the universe is silent, the next, it screams. Fast radio bursts, or FRB, are the cosmos' most fleeting and furious enigmas. Blasts of radio waves so intense they outshine entire galaxies, yet so brief they vanish in milliseconds. Picture the sun releasing days' worth of energy in the time it takes to blink, and you're close to the raw power of these cosmic fireworks. But here's what really stumps scientists: we don't know what's setting them off. The first FRB was caught by accident in 2007, buried in old telescope data like a cosmic breadcrumb. Since then, hundreds more have been detected, each one a puzzle wrapped in static. Some burst once and never reappear, like a door slamming shut in deep space. Others repeat with erratic timing, dashing hopes of finding a predictable rhythm. Take FRB 121102, the first known repeater, which fires off signals from a dwarf galaxy 3 billion light-years away. Its bursts vary wildly in strength, as if some capricious cosmic hand is flicking a switch on and off at random. So what could possibly generate such violent, fleeting energy? The prime suspects are magnetars, neutron stars with magnetic fields so strong they'd erase a credit card from 500,000 miles away. When these stars crack under the strain, like a tectonic plate shifting, they might unleash FRBs in colossal stellar quakes. Then there's the cosmic comb theory. As a neutron star's powerful wind plows through surrounding gas, it could create shock waves that focus radio energy into tight, explosive beams. But not all explanations stay within the bounds of known physics. Some FRBs arrive with bizarre substructures, tiny pulses within pulses, as if they've been encoded with complex information. That's led to inevitable speculation. Could these be signatures of advanced civilizations, harnessing unimaginable energy to power interstellar beacons? While the odds are slim, the sheer strangeness of FRBs forces scientists to keep even the wildest ideas on the table. The real frustration lies in their elusiveness. By the time telescopes swing toward an FRB's origin, the trail's gone cold. New observatories like the CHIME Array in Canada are racing to catch them in the act, scanning vast swaths of sky every night. Each detection peels back another layer of the mystery, revealing more questions than answers. Why do some FRBs skew younger, appearing in turbulent star-forming galaxies, while others lurk in quieter cosmic neighborhoods? Why do a rare few arrive with a trailing afterglow of lower frequency waves like an echo in the dark? Every burst feels like a message in a bottle tossed across billions of light years. The urgency to decode them isn't just academic, it's a chance to probe the most extreme environments in the universe where matter and energy behave in ways we've barely dreamed of. Until then, FRBs remain cosmic Morse code, tapping out a question we're still learning how to ask. Every second, Earth is under siege from the cosmos, not by asteroids or alien probes, but by invisible bullets of pure energy. Cosmic rays are atomic fragments racing through space at nearly the speed of light, some packing a punch so fierce they dwarf anything humanity's most powerful particle accelerators can create. Imagine a single proton, smaller than an atom, carrying the kinetic energy of a baseball hurled at 60 miles per hour. Now multiply that by 100 million, and you're close to the brute force of the most extreme cosmic rays ever detected. These aren't just random space debris, they're messengers from the universe's most violent corners, and decoding their origins could rewrite the rules of particle physics. For over a century, scientists have chased these ghostly projectiles, tracing their paths back through tangled magnetic fields across the galaxy. The puzzle begins with their staggering diversity. Most cosmic rays are relatively low-energy protons, likely accelerated by shock waves from exploding stars. But the real head-scratchers are the ultra-high-energy cosmic rays, rare particles so powerful they shouldn't exist. According to Einstein's special relativity, particles from distant galaxies should lose energy as they collide with photons from the cosmic microwave background, a phenomenon called the Greisen-Zatsepin-Kuzmin cutoff. Yet detectors like the Pierre Auger Observatory in Argentina keep catching cosmic rays that blow past this theoretical speed limit, as if the universe is flinging impossibly fast fastballs right at us. So what cosmic slingshot could launch particles with such violence? Supermassive black holes are prime suspects, their accretion disks acting like natural particle accelerators. When matter spirals into these gravitational monsters, magnetic fields might whip particles to near-light speeds, ejecting them in jets spanning millions of light years. Another contender, active galactic nuclei, where entire galaxies glow brighter than 1 trillion suns, their cores seething with turbulence that could catapult particles across the cosmos. Even more exotic explanations lurk in the shadow's cosmic strings, defects in spacetime from the Big Bang, or decaying dark matter particles annihilating in bursts of energy. The hunt for answers plays out in some of Earth's most remote landscapes. At the Auger Observatory, 1,600 water tanks sprawl across 3,000 square kilometers of Argentine prairie, waiting for the faint blue glow of Cherenkov radiation, a telltale sign of a cosmic ray striking the atmosphere. Meanwhile, orbiting detectors like the Alpha Magnetic Spectrometer on the International Space Station sift through particles directly, filtering out interference from Earth's magnetic field. Despite these efforts, cosmic rays remain frustratingly coy. Their paths bend in interstellar magnetic fields, masking their origins like a bullet ricocheting before it hits its target. The implications stretch far beyond astrophysics. Some researchers speculate that high-energy cosmic rays could have played a role in Earth's biological evolution, triggering mutations by zapping DNA in primordial organisms. Others wonder if they pose a stealth hazard to future Mars colonists, bathing the planet's surface in radiation we're only beginning to quantify. But the deepest allure lies in the unknown. Each ultra-high-energy particle is a fingerprint from processes we can't yet replicate, a challenge to our understanding of nature's extremes. Until we crack their code, these microscopic invaders will keep raining down, silent and relentless, carrying secrets from the darkest corners of the universe. The sheer numbers alone should make the universe feel crowded. With hundreds of billions of galaxies, each containing billions of stars and countless planets orbiting in habitable zones, the cosmos seems primed for life. Statistically, we shouldn't just be hunting for microbes on Mars, we should be tripping over interstellar neighbors. Yet when we point our telescopes skyward and listen for whispers of alien technology, the silence is deafening. This glaring contradiction between probability and reality is the heart of the Fermi paradox, a riddle that's haunted scientists since physicist Enrico Fermi famously asked over lunch in 1950, "Where is everybody?" Consider how much cosmic real estate could host civilizations older and wiser than our own. Earth is a relative newcomer. Life here took nearly 4 billion years to produce a species capable of broadcasting radio waves. Meanwhile, some exoplanets orbit stars billions of years older than the Sun. If intelligence evolves even slightly faster elsewhere, entire civilizations could have risen and fallen before Earth's first microbes appeared. By now, their descendants might have harnessed the energy of stars, built megastructures detectable across light years, or even mastered interstellar travel. So why does every SETI scan come up empty? The answers we've conjured range from sobering to spine-chilling. One leading theory, the Great Filter, suggests some catastrophic bottleneck prevents life from reaching the stars. Maybe the leap from single-celled organisms to complex life is astronomically rare, or perhaps intelligent life inevitably destroys itself through climate collapse, nuclear war, or unchecked artificial intelligence. The terrifying twist: if we don't find fossils on Mars, it might mean the Great Filter still lies ahead of us, waiting to snuff out civilizations like ours before they spread beyond their home systems. But not all explanations paint such a grim picture. Some argue advanced civilizations might simply be undetectable by our primitive instruments. Imagine an alien race that communicates via neutrino beams or quantum entanglement technologies we're only beginning to fathom. Others propose the zoo hypothesis, that extraterrestrials intentionally avoid contact, observing us like wildlife in a cosmic sanctuary until we reach some ethical or technological threshold. There's even the unsettling notion that we're alone, that Earth is a freakish outlier in an otherwise sterile universe where the chemical dice rolled in our favor just once. The most radical solutions rewrite the rules entirely. Could we be living in a simulation where extraterrestrials were never programmed into the code? Or might spacefaring cultures have transcended physical form, uploading their consciousness into Dyson spheres or black hole computers, leaving no electromagnetic trace? The longer the silence persists, the more we're forced to confront an uncomfortable truth. The universe doesn't owe us company. Its silence might be the greatest lesson of all, a humbling reminder that life, or at least intelligence, could be far more fragile and fleeting than we dare admit. Yet the search continues. Projects like Breakthrough scan millions of stars for synthetic radio pulses, while astronomers scour telescope data for irregular starlight that might indicate alien megastructures. Each null result tightens the paradox, sharpening the question Fermi posed decades ago. Whether the answer brings solitude or salvation, one thing's certain: the cosmos has never felt so vast or so enigmatic. One of Einstein's greatest grudges against quantum mechanics wasn't its complexity, it was its audacity to defy common sense. He famously ridiculed the idea of quantum entanglement as spooky action at a distance, a phrase that stuck precisely because it captures how unnerving this phenomenon truly is. Picture two electrons born from the same quantum event, spiraling away from each other across the galaxy. According to the rules of entanglement, measuring one, say, finding its spin pointing up would instantly force its twin into the opposite state, no matter how far apart they've traveled. No signal passes between them, no hidden wires connect them. The change happens faster than light, as if the universe itself forgot to obey the speed limit. The implications are staggering. For decades, physicists argued whether this was evidence of flaws in quantum theory or proof of a reality far stranger than Einstein could stomach. Then came the experiments. In 1982, a lane aspect fired entangled photons in opposite directions and measured their properties at detectors several meters apart. The results were unequivocal. The particles acted in perfect, instantaneous sync, violating classical notions of locality. Later tests closed every conceivable loophole, stretching the distance to over 1,000 kilometers using satellites. The verdict: entanglement is real, and the universe doesn't care that it breaks our intuition. But here's where things get even weirder. Entanglement isn't just a quirk of tiny particles. It might be woven into the fabric of spacetime itself. Some theories suggest that the very geometry of the universe emerges from a vast, underlying network of entangled quantum states. Think of spacetime as a cosmic tapestry, with every thread connected in ways we can't directly see. Black holes, those ultimate cosmic shredders, might preserve information through entanglement, their event horizons encoding data in ways that defy classical destruction. Even gravity, the last holdout of classical physics, could be an emergent property of quantum entanglement, a collective behavior of microscopic links we're only beginning to map. The technological promise is equally mind-bending. Quantum computers harness entangled qubits to perform calculations that would take conventional machines millennia, cracking encryption or simulating molecular interactions with ease. Then there's the tantalizing but controversial idea of quantum communication. Could entangled particles transmit information faster than light? The math says no. You can't force a measurement to yield a specific outcome, and any attempt to encode a message would break the entanglement. But what if we're missing something? The history of quantum mechanics is littered with impossible ideas that later became foundational. Perhaps the most profound lesson of entanglement isn't about technology, it's about reality itself. The universe seems to operate on a level of interconnectedness that renders our classical notions of separation obsolete. Two particles can be light years apart yet remain a single, indivisible system. This isn't just science, it's philosophy written in the language of mathematics. Are we looking at a cosmic glitch or the first clue to a deeper layer of existence where distance and individuality are illusions? The spookiness isn't in the action, it's in the realization that we're only beginning to glimpse the rules of the game. Imagine throwing a book into a fire. The pages curl and blacken, the ink vanishes, but in theory, every word could be reconstructed from the smoke and ash if you had perfect knowledge of the physics involved. That's the core promise of quantum mechanics. Information is never truly lost, just transformed. Now picture that book falling into a black hole. According to Einstein's general relativity, the book, and every bit of information it contained, is crushed into the singularity, a point of infinite density where the laws of physics break down. Gone, erased, this cosmic censorship poses no problem for classical physics, but it sends quantum theory into crisis. The conflict between these two frameworks isn't just academic, it's a battle for the soul of reality itself, and the stakes couldn't be higher. Enter Stephen Hawking. In the 1970s, he made a startling prediction. Black holes aren't completely black. They emit radiation, slowly leaking energy until they evaporate entirely. This revelation should have been the solution. If radiation carries energy out of the black hole, perhaps it also carries scrambled fragments of the original information. But Hawking's math suggested otherwise. The radiation appeared random, thermal, devoid of any meaningful structure. If he was right, the information really was destroyed, violating a fundamental tenet of quantum mechanics. The scientific community split into warring camps. Some, like Hawking, bet that information was irrevocably lost. Others, like Leonard Susskind, insisted the universe must find a way to preserve it, even if we couldn't yet see how. The tension birthed the black hole information paradox, a puzzle so profound its resolution could redefine our understanding of space, time, and the nature of information itself. One promising avenue comes from holography. the idea that all the information within a black hole's volume might be encoded on its two-dimensional event horizon, like a cosmic DVD. String theory takes this further, suggesting that falling matter doesn't actually reach the singularity. Instead, it smears into a fuzzball of vibrating strings at the horizon, its information forever hovering just out of reach. Then there's the firewall paradox. If information does escape via Hawking radiation, quantum mechanics demands that the event horizon becomes a seething wall of high-energy particles, incinerating anything crossing it. But this contradicts relativity's claim that falling into a black hole should feel uneventful, no fireworks, just the quiet pull of gravity. The debate rages on, with recent breakthroughs in quantum gravity offering glimpses of a possible middle ground. Some researchers propose that black holes are quantum error-correcting codes, their radiation subtly entangled in ways that preserve information without violating known laws. What makes this paradox so captivating isn't just the theoretical stakes, it's the sheer audacity of the questions it forces us to ask. Is spacetime itself an illusion emerging from deeper quantum interactions? Do black holes punch holes in causality or reveal its true structure? Every proposed solution peels back another layer of the unknown, reminding us that even the most extreme objects in the universe are still bound by rules we're only beginning to decipher. Until we crack the code, black holes will remain cosmic enigmas, whispering secrets just beyond the edge of understanding. Deep within the corpse of a dead star, a catastrophe is brewing. Neutron stars, the leftover cores of exploded supernova, are so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Their surfaces, forged under unimaginable pressure, shouldn't crack. Yet they do violently. These cosmic tremors, called Starquakes, unleash energy equivalent to a magnitude 32 earthquake, sending ripples through spacetime itself. The mechanics are as bizarre as they are brutal. Picture a neutron star's crust, a lattice of atomic nuclei packed so tightly they form a crystalline shell harder than diamond. Beneath it swirls a superfluid ocean of neutrons, frictionless and chaotic. When the star's insane magnetic field, trillions of times stronger than Earth, shifts or fractures the crust, the entire structure lurches. The result, a glitch, a sudden, unpredictable change in the star's rotation speed, as if the universe hit a cosmic pause button. Some glitches slow the star down. Others speed it up by milliseconds, enough to fling tsunamis of gravitational waves across the galaxy. But what snaps under all that pressure? One theory points to vortices in the superfluid core. Normally, these whirlpools align with the star's spin. But if they suddenly break free and slam into the crust, the transfer of momentum could trigger a quake. Alternatively, the crust itself might accumulate stress like tectonic plates, buckling under strain until it fractures like a frozen lake in winter. Then there's the wild card, magnetic reconnection, where twisted field lines explosively reconfigure, releasing enough energy to jolt the star's entire surface. Detecting these events is like listening for a whisper in a hurricane. Gravitational wave observatories like LIGO hunt for the faint distortions caused by starquakes, while radio telescopes monitor pulsars, rapidly spinning neutron stars that beam lighthouse-like signals. When a glitch occurs, the pulsar's rhythm hiccups, betraying the turmoil within. In 2019, astronomers caught one mid-quake. A pulsar named J1838 slowed abruptly, then began recovering over months, a clue that its superfluid interior was rebalancing like a gyroscope finding its footing. The implications stretch far beyond stellar curiosities. These ultra-dense objects are nature's laboratories, testing matter under conditions no collider can replicate. Does their core contain exotic particles like hyperons or deconfined quarks, dissolving the very idea of protons and neutrons? Starquakes could be our only window into physics at these extremes. Each tremor is a message in a bottle written in space-time, carrying secrets from a realm where the rules we know don't just bend, they shatter. On a quiet Ohio night in 1977, a radio telescope scanning the stars for signs of extraterrestrial intelligence caught something extraordinary, a 72-second burst of radio waves so powerful that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that single word would immortalize the signal as one of the most tantalizing mysteries in the search for cosmic companions. Even today, decades later, no natural or human-made phenomenon fully explains it. The signal's intensity was off the charts, 30 times stronger than the background noise of deep space, and it appeared to originate near a star group in Sagittarius, precisely the kind of quiet cosmic neighborhood where a civilization might broadcast a deliberate hello. What sets the WOW signal apart from other cosmic static is its uncanny structure. It occupied a narrow frequency band around 1420 MHz, a range scientists had flagged as ideal for interstellar communication because it's relatively free of interference from cosmic gases. Even stranger, the signal's strength rose and fell in a pattern mirroring what you'd expect if it were sweeping past Earth due to a distant planet's rotation. Then, just as abruptly as it began, it vanished, never to repeat despite constant monitoring of the same patch of sky, theories attempting to explain its swing from pragmatic to spine-tingling. Some argue it was a fleeting event, like a comet's hydrogen cloud emitting radio waves as it passed through the telescope's field of view. In 2017, researchers pointed to two comets that hadn't been catalogued at the time, suggesting their gases could mimic the signal. But subsequent analysis showed their trajectories didn't match up, and comets don't typically produce such intense, focused bursts. Others propose an exotic cosmic coincidence, perhaps a natural maser, an interstellar amplifier created by excited molecules briefly aligned with Earth. Then there's the electrifying possibility. The WOW signal was intentional. Imagine a civilization with technology just a few centuries ahead of ours, aiming a high-powered transmitter our way. Unlike Hollywood's idea of continuous broadcasts, a targeted pulse would be energy efficient. A 72-second burst detectable across light years could be a cosmic ping, an exploratory probe disguised as noise. The kicker, if it came from a star system 150 light-years away, any reply we send now wouldn't reach them until the 22nd century. The signal's enduring allure lies in its refusal to fit neatly into any category. It's too clean for natural interference, too brief for confirmation, and too perfectly placed to dismiss. Every new analysis, whether hunting for echoes in archival data or testing modern telescopes against its profile, only deepens the mystery. Projects like Breakthrough Listen now comb through millions of radio channels, hoping to catch another whisper. Until then, the WOW signal stands as a cosmic Rorschach test, inviting us to project our hopes and fears onto the blank canvas of the universe's silence. Whether it was a celestial fluke or a deliberate nudge, one thing's certain: it proves the universe knows how to keep a secret. Tabby's star doesn't flicker, it plummets. Most stars dip in brightness by a fraction of a percent when planets transit their faces. But this one, formerly known as KIC 8462852, drops by up to 22% at irregular intervals, as if something colossal and shapeless is drifting between it and Earth. The first time astronomers saw this data from the Kepler Space Telescope, they assumed it was a glitch. Rechecking the numbers only deepened the mystery. Here was a star 1,200 light-years away in the constellation Cygnus, behaving like no other in the cosmos. The initial explanation pointed to a swarm of comets, thousands of them, maybe even millions, in a chaotic dance around the star. Such a debris field could theoretically block starlight in unpredictable ways, but the math never quite added up. For comets to cause dips this severe, they'd need to be far larger and more numerous than anything observed in our own solar system. Worse, follow-up studies revealed something even stranger. Tabby's star isn't just dimming sporadically. Over the past century, its overall brightness has faded by as much as 14%, a decline no known natural process can easily explain. That's when the speculation took a sharp turn toward science fiction. Could this be evidence of alien engineering? The idea isn't as far-fetched as it sounds. In the 1960s, physicist Freeman Dyson proposed that advanced civilizations might build vast energy-collecting structures around their stars' megastructures called Dyson spheres or rings. Fragments of such constructs, still under construction or in disrepair, might account for the star's erratic dimming. The hypothesis gained enough traction to prompt targeted searches for laser signals or other technosignatures from the system. So far, silence, but alternative theories keep pushing the boundaries of astrophysics. Maybe the star is surrounded by a colossal disk of planet-forming dust, warped into spirals by an unseen companion. Or perhaps it recently devoured a gas giant, leaving behind a tempest of debris. Some researchers even suggest it's passing through an interstellar dust cloud, though why that wouldn't affect neighboring stars remains unclear. The most compelling recent data points to something far simpler, yet still puzzling: ultrafine dust. Observations from the Hubble and Spitzer telescopes show the dimming is more pronounced in ultraviolet than infrared, a fingerprint of tiny particles smaller than a grain of flour. But here's the catch: such dust should be blown away by stellar radiation within years. Its persistence implies an ongoing source, like the grinding of moon-sized asteroids or the vaporization of icy bodies in eccentric orbits. Tabby's star refuses to fit into a neat box. Every new observation adds layers to the enigma, forcing us to question whether we're seeing cosmic vandalism, a star being dismantled by gravity or collision, or something far more deliberate. The longer it defies explanation, the more it underscores how little we truly understand about the lives and deaths of stars. For now, it remains a celestial Rorschach test, revealing as much about our hunger for discovery as it does about the unknown phenomena lurking in the deep sky. In the vast emptiness of space, where every gram of thrust matters, the tiniest deviation from expected motion can rewrite physics textbooks. That's exactly what happened with NASA's Pioneer 10 and 11 probes, twin explorers launched in the early 1970s to study Jupiter, Saturn, and the void beyond. For decades, as they hurtled toward the edges of the solar system, scientists noticed something odd: both spacecraft were slowing down just a hair more than they should have been. Not by much, just enough to lag behind their projected positions by about 300,000 miles over 20 years, the equivalent of a car coasting to a stop a few inches sooner than calculated. But in the precision-driven world of orbital mechanics, even an anomaly this slight was enough to spark a crisis in cosmology. At first, the explanation seemed mundane. Maybe heat radiating unevenly from the probe's nuclear power sources was giving them a tiny push in the wrong direction, like a tea kettle whistling steam sideways. Or perhaps residual fuel was leaking from unseen cracks in their thrusters, bleeding momentum into space. Yet when engineers crunched the numbers, these effects couldn't account for the full discrepancy. That left a far more tantalizing possibility. Was there some unseen force tugging at the Pioneers, some cosmic undercurrent we hadn't accounted for? Theories proliferated like starbursts. Could dark matter be pooling in our solar system, its gravity dragging on the probes? Or was Einstein's theory of general relativity incomplete at these vast scales, requiring tweaks to how gravity behaves in the outer solar system? A handful of researchers even floated the idea of modified Newtonian dynamics, Ormond, a controversial framework suggesting gravity strengthens slightly at extremely low accelerations, exactly the regime where the Pioneers were traveling. The implications were staggering. If true, it meant our entire understanding of celestial mechanics was missing a footnote. Then, in 2012, decades after the anomaly was first spotted, painstaking analysis of old engineering data revealed the culprit: thermal recoil. Heat from the probe's electrical systems was radiating unevenly, after all, not from their power sources, but from their instrument panels and antennae. The cumulative effect was like a minuscule rocket engine firing in reverse, slowing the Pioneers bit by bit. Case closed, not quite. While thermal recoil explained most of the anomaly, some scientists argued it couldn't account for all the deceleration, leaving a sliver of the mystery unresolved. The Pioneers' legacy isn't just about solved puzzles, it's a masterclass in scientific humility. These spacecraft taught us that even the quietest whispers of data can challenge our grandest theories, that the universe leaves crumbs of contradiction in the most unexpected places. Today, as new probes like New Horizons race toward interstellar space, they carry upgraded instruments designed to measure every photon of heat, every molecule of outgassing, ensuring we don't miss the next subtle clue. Because sometimes it's not the blazing supernova that change our understanding of reality, it's the faintest tug in the dark. If black holes are the universe's ultimate vacuum cleaners, then white holes are their rebellious twins, cosmic fire hydrants blasting matter outward with unstoppable force. These hypothetical monsters, born from the same equations that predict black holes, flip the script entirely. Nothing can enter a white hole, only exit at speeds approaching light. Picture a black hole in reverse, a cosmic exhaust pipe where the universe's trash might come shooting back out. But here's the catch: while black holes are everywhere, from galaxy centers to sci-fi plots, white holes remain pure mathematical phantoms. Not a single one has ever been spotted, leaving physicists to wonder, are they hiding in plain sight, or are they just beautiful mirages in the equations? The idea traces back to Einstein's general relativity, where the math allows for symmetrical solutions. If a black hole singularity crushes matter into oblivion, a white hole singularity would vomit it back out, potentially including everything the black hole ever swallowed. Some theories suggest white holes could be the other end of wormholes, acting as gateways between distant regions of spacetime. Even wilder is the notion that the Big Bang itself might have been a white hole event, a primordial eruption of matter and energy from some unknowable elsewhere. But why the cosmic radio silence? One possibility is that white holes are spectacularly unstable. Unlike their black hole siblings, which greedily hoard mass, white holes would violently repel anything trying to feed them, including their own energy. Calculations suggest they might collapse almost instantly into black holes, like a balloon popping the moment it inflates. Others argue they could exist in quantum realms, flickering in and out of existence at scales too tiny to detect. Then there's the observational paradox. If white holes spew out radiation and matter, why don't we see cosmic fireworks matching their descriptions? Some researchers speculate that gamma-ray bursts, the most energetic explosions since the Big Bang, could be dying gasps of white holes. Others wonder if dark matter's gravitational effects might hint at their presence, invisible but undeniable. The most tantalizing clue might come from black hole evaporation. As Hawking radiation slowly drains a black hole's mass, could its final moments rebirth it as a white hole in a final burst of cosmic recycling? The math hints at this poetic symmetry, but nature rarely obeys our storytelling instincts. White holes force us to confront the limits of theory versus reality. They're a reminder that the universe's playbook might contain chapters we haven't even imagined, phenomena lurking in the shadows of equations, waiting for a telescope brave enough to prove them real. Until then, they remain the ultimate cosmic thought experiment. What if existence has an undo button? The universe is supposed to be a vast, indifferent expanse, no preferred direction, no cosmic landmarks, no hidden axis guiding its structure. That's the cosmological principle in a nutshell, the idea that on the largest scales, matter and energy are spread evenly, with no special place or orientation. But in 2005, astronomers studying the most ancient light in existence, the cosmic microwave background, or CMB, stumbled upon something that shouldn't be there. A bizarre, sprawling pattern in the afterglow of the Big Bang itself, a strange alignment of hot and cold spots stretching across the sky like a ghostly highway. They called it the axis of evil, and its very existence threatens to crack the foundation of modern cosmology. This isn't just a minor statistical hiccup. The CMB is our universe's baby picture, a snapshot from when it was just 380,000 years old, its photons finally free to travel after the fog of primordial plasma cleared. According to the standard model, those temperature fluctuations should be random, like static on an old television. No order, no hidden structure. Yet when researchers mapped them, they found an eerie correlation. The fluctuations seemed to line up along a specific axis, as if the universe had a subtle tilt. Even stranger, this axis roughly aligns with our solar system's orientation, a coincidence so improbable it smells either of groundbreaking discovery or colossal error. Theories to explain it range from the mundane to the mind-bending. Could it just be contamination from our own Milky Way's dust or foreground emissions? Detailed studies say no, the signal persists even after accounting for local interference. Maybe it's an artifact of how we process the data, a subtle bias in the algorithms used to pass the CMB's faint whispers. Yet independent teams using different instruments and methods keep finding the same pattern. Then come the wilder possibilities. Some physicists suggest the axis of evil might be a cosmic bruise, evidence of a collision with another universe in the multiverse, a gravitational imprint left by something beyond our spacetime. Others propose it's a remnant of pre-Big Bang physics, a fingerprint of whatever existed before inflation erased nearly all traces of the universe's birth. The most radical idea, that we're seeing the shadow of a giant primordial magnetic field woven into the fabric of reality before the first stars flickered to life. The implications are staggering. If the universe has a preferred direction, it means our most basic assumptions about its origins are incomplete or flat out wrong. Dark energy, dark matter, even the Big Bang's initial conditions might need rethinking. The Planck satellite, with its ultra-precise CMB measurements, was supposed to settle the debate. Instead, it deepened the mystery, confirming the anomaly with higher resolution but no clearer explanation. For now, the axis of evil remains a thorn in cosmology's side, a shadow at the edge of our understanding. Whether it's a flaw in our models or a crack in reality itself, one thing's certain: the universe loves to surprise us, and sometimes its most unsettling surprises come dressed as faint ripples in the oldest light we'll ever see. ʻOumuamua wasn't just another space rock, it was an interloper from the stars, the first confirmed visitor from beyond our solar system. When astronomers spotted it in October 2017, it was already racing away from us at nearly 200,000 miles per hour, its trajectory screaming interstellar. But this wasn't just any cosmic hitchhiker. Its shape alone defied logic, long and needle-like, up to 10 times as long as it was wide, tumbling end over end like a cigarette tossed in zero gravity. Nothing in our solar system, no asteroid, no comet looks like that. And then came the real shock. As it hurtled past the sun, ʻOumuamua sped up slightly, as if nudged by an invisible hand. The acceleration sent scientists scrambling. Comets often get a boost from outgassing. Sunlight vaporizes their ices, creating jets that act like natural thrusters. But ʻOumuamua showed no coma, no tail, no dusty plume. It was dark, reddish, and eerily quiet. Some argued it might be a dark comet, venting pure hydrogen gas trapped in its icy interior, a phenomenon never before seen. Others proposed it was a shard of nitrogen ice sheared off a Pluto-like exoplanet, evaporating silently as it fled the sun's warmth. Each explanation felt like forcing a square peg into a round hole. Then came the whispers of something more exotic. Harvard astronomer Avi Loeb famously floated the possibility, controversial but irresistible, that ʻOumuamua could be artificial, a light sail fragment from an alien civilization, thin and reflective, pushed by starlight. The idea wasn't entirely outlandish. Humanity's own light sail project proves the concept works, but without a clear radio signature or other technosignatures, the hypothesis remained in the realm of tantalizing speculation. What makes ʻOumuamua so perplexing isn't just its strangeness, it's the realization of how little we know about interstellar objects. For centuries, we've studied planets, comets, and asteroids born from the same cosmic nursery as Earth. ʻOumuamua was forged around another star under conditions we can only guess at. Was it ejected during a planetary collision, torn from an alien Kuiper belt by a passing star? Every answer raises new questions. The real tragedy: we barely had time to look. By the time telescopes swung toward it, ʻOumuamua was already too faint for detailed imaging. Future interstellar visitors might slip past unnoticed unless we ramp up sky surveys. Projects like the Vera Rubin Observatory, with its ultra-wide field camera, could catch the next one earlier, giving us precious weeks to study its composition, rotation, and chemistry. Until then, ʻOumuamua remains a cosmic cipher, a fleeting glimpse of the untold wonders drifting between the stars just beyond our reach. At the heart of modern physics lies a glaring contradiction so fundamental it keeps theorists awake at night. On one hand, Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, continuous landscape where planets and stars dance along invisible grooves. On the other, quantum mechanics describes a chaotic subatomic world where particles pop in and out of existence, where uncertainty reigns and nothing is truly fixed. Both theories work flawlessly within their domains. Relativity guides GPS satellites and predicts black holes, while quantum mechanics powers smartphones and explains chemical bonds. But when these titans collide at the edge of black holes or the first moments of the Big Bang, the math implodes into gibberish. The universe, it seems, operates by two irreconcilable rulebooks, and bridging that gap is the single greatest challenge in theoretical physics. Enter string theory, perhaps the most famous contender in the quest for quantum gravity. It proposes a radical rewrite of reality's building blocks, tiny, vibrating strings whose oscillations give rise to every particle and force in existence. In this framework, even gravity emerges from the dance of these strings, neatly unifying all fundamental interactions. But there's a catch: string theory demands 10 or 11 dimensions, most curled up into spaces smaller than an atom. Worse, it predicts a near-infinite number of possible universes, with no clear way to test which one, if any, corresponds to our own. For all its mathematical elegance, string theory remains a gorgeous castle built on experimental quicksand. Then there's loop quantum gravity, string theory's scrappier rival. Instead of extra dimensions, it chops spacetime itself into discrete, indivisible chunks, a cosmic pixelation at the Planck scale. Picture the universe as a vast network of intersecting loops where gravity arises from their quantum interactions. This approach keeps spacetime firmly in the quantum realm, but struggles to explain how smooth spacetime emerges from this granularity at larger scales. While string theory dreams of hidden dimensions, loop quantum gravity grapples with how our familiar 4 dimensions knit together. Other ideas push the boundaries even further. Causal dynamical triangulations treat spacetime as a mosaic of tiny geometric shapes that dynamically rearrange themselves. Entropic gravity suggests gravity isn't a fundamental force at all, but an emergent side effect of entropy and information storage at the universe's edges. Each approach shines light on different facets of the problem, but none have delivered the knockout blow, a prediction so precise and testable that it silences all doubt. The stakes couldn't be higher. Without a theory of quantum gravity, we're blind to the universe's most extreme environments. What really happens at the singularity inside a black hole? What ignited the Big Bang? These aren't just academic musings. The answers could rewrite our understanding of causality, information, and the very nature of time. Some theories suggest space-time itself might be an illusion, a holographic projection from a deeper reality. Others hint that quantum entanglement could weave the fabric of space-time together, stitch by stitch. For now, experiments lag woefully behind theory. Detecting quantum gravity's subtle whispers would require probes with energies 1 trillion times beyond today's particle colliders, or telescopes sensitive to quantum fluctuations in distant black hole mergers. But next-generation instruments like gravitational wave detectors with atomically precise lasers might finally catch the faintest tremors of quantum spacetime. Until then, physicists navigate by mathematical intuition, chasing the faintest glimmers of a theory that could crown one of history's greatest scientific revolutions, or force us to tear up the map and start anew. The universe is expanding, this much we know, but how fast? That's where things get messy. For decades, astronomers assumed measuring the cosmos' growth rate would be straightforward. Point telescopes at distant galaxies track their movement and crunch the numbers, but in recent years, a glaring inconsistency has emerged, shaking the foundations of cosmology. Depending on how you measure it, the universe's expansion rate, known as the Hubble constant, gives two stubbornly different answers. This rift, nicknamed the Hubble tension, isn't just a minor discrepancy. It's a full-blown crisis, forcing scientists to question whether we've misunderstood dark energy, overlooked hidden forces, or even misread the cosmos' history. Start with the local method, measuring the Hubble constant by observing pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies. These cosmic yardsticks have known brightness, letting astronomers calculate distances with precision. The latest data from the Hubble Space Telescope and Gaia satellite pegs the expansion rate at roughly 73 kilometers per second per megaparsec. That means for every additional megaparsec, about 3.3 million light-years a galaxy is from us, it appears to recede 73 kilometers per second faster. Simple, right? Now switch to the early universe approach, analyzing the cosmic microwave background, the afterglow of the Big Bang. Using missions like Planck, scientists extrapolate the Hubble constant from the CMB's subtle temperature fluctuations, which reflect the universe's infant geometry. This method lands on a slower value around 67 kilometers per second per megaparsec. The difference seems small, but in cosmology, even a few percent can upend everything. If both methods are flawless, the gap implies something fundamental is missing from our models, or worse, that the laws of physics themselves change over cosmic time. So where does the tension come from? One camp argues for observational errors. Perhaps Cepheids are trickier to calibrate than we thought, or supernovae aren't as uniform as assumed. Yet repeated studies keep confirming the mismatch, narrowing the odds of a mere measurement fluke. Another possibility is that dark energy isn't constant, as Einstein's cosmological constant presumes, but evolves, subtly tweaking the expansion rate over billions of years. Or maybe there's an unknown particle, a dark radiation, like sterile neutrinos zooming through space-time, altering the early universe's energy balance. The wildest theories go further. Could our patch of the universe sit inside a rare underdense bubble, locally skewing measurements? Or is gravity itself behaving differently on vast scales, echoing the anomalies seen in galactic rotations? Each hypothesis carries radical implications. If dark energy strengthens with time, it could spell a Big Rip scenario, tearing atoms apart. If new particles exist, they demand a rewrite of the standard model. The Hubble tension isn't just academic quibbling. It's a crack in the edifice of modern cosmology, Upcoming telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope aim to settle the debate with sharper data. But until then, the disagreement stands as a humbling reminder. The universe excels at defying our neatest theories, leaving us to puzzle over the gaps between what we see and what we think we know. Time crystals sound like something ripped from a sci-fi novel, structures that repeat not in space, but in time, ticking like quantum metronomes without any energy input. Unlike ordinary crystals, where atoms arrange in repeating patterns like a lattice of salt or diamond, time crystals flip the script entirely. Their atoms oscillate in a never-ending cycle, returning to their original state at fixed intervals, as if the universe itself hit a mysterious rewind button. The craziest part, they do this without violating the laws of thermodynamics. No energy is created or lost, the system just keeps moving, a perpetual dance frozen in the lowest possible energy state. When Nobel laureate Frank Wilczek first proposed the idea in 2012, physicists met it with skepticism. How could anything exhibit periodic motion indefinitely without an energy source? It sounded suspiciously close to the forbidden dream of perpetual motion. But by 2017, labs at Harvard and the University of Maryland had done the impossible. They built time crystals using chains of ytterbium ions and diamond impurities chilled to near absolute zero. The key was breaking time translation symmetry, a fancy way of saying the system's ground state doesn't look the same at all times, unlike conventional matter. Hit it with a laser pulse and the atoms start flipping in a predictable rhythm, locked in a loop that repeats like clockwork. What makes time crystals so revolutionary isn't just their defiance of classical intuition, it's their potential to rewrite the rules of quantum computing. Imagine a quantum memory so stable it resists decoherence, the kryptonite of quantum systems. Time crystals' inherent periodicity could act as a built-in error correction system, shielding fragile qubits from the chaos of their surroundings. Or picture sensors of unimaginable precision, tapping into these oscillations to detect infinitesimal changes in magnetic fields or gravity. Some theorists even speculate they could unlock new phases of matter, states so exotic they don't fit into the traditional solid, liquid, gas, plasma categories. Yet the wildest possibilities lurk in the theoretical shadows. Could time crystals hint at deeper symmetries in the fabric of reality, where time itself behaves differently at quantum scales? Wilczek once mused about space-time crystals with structures repeating in both space and time, a notion that edges into speculative physics. And while they're not perpetual motion machines in the classic sense, they can't do work or output energy. They do prove that nature permits motion without energy decay, a revelation that already has physicists questioning what other, impossible phenomena might be hiding in plain sight. For now, time crystals remain lab curiosities, fragile and fleeting, but their very existence is a thunderclap, a reminder that the universe's playbook is far stranger than we imagined. Every flicker of their rhythmic atoms whispers a tantalizing question. What else have we missed? Galactic cannibalism sounds like something from a cosmic horror story, and in a way it is. Across the universe, galaxies engage in a slow, violent dance of consumption, where the strong devour the weak, reshaping the cosmos over billions of years. Picture a spiral galaxy like our Milky Way, serene and majestic, its arms swirling with stars. Now imagine it stretching out gravitational tendrils, ensnaring a smaller, hapless dwarf galaxy, tearing it apart until its stars are absorbed into the larger structure. This isn't science fiction, it's the reality of how galaxies grow, and it's happening all around us. The process is as brutal as it is beautiful. When a larger galaxy merges with a smaller one, gravity does the dirty work. Tidal forces stretch the victim into ribbons, scattering stars into long, looping streams called tidal tails. Some stars are flung into the void, while others settle into chaotic orbits around the cannibal. The Milky Way's own halo is littered with these remnants, ghosts of past meals. One of the most dramatic examples is the Gaia sausage, the splattered remains of a dwarf galaxy that collided with ours billions of years ago. Named for its sausage-like shape in stellar motion data, this ancient merger left behind a swarm of stars orbiting at odd angles, a fossilized record of cosmic violence. But galactic cannibalism isn't just about destruction, it's also a catalyst for creation. The influx of fresh gas and dust from devoured galaxies can trigger bursts of star formation, lighting up the cannibal with newborn stars. Supermassive black holes at the centers of galaxies also feast during these mergers. As material spirals inward, it heats up, unleashing brilliant quasars, some of the brightest objects in the universe. The Milky Way's own central black hole, Sagittarius A, likely gorged during past mergers, flaring up as it swallowed stars and gas. The consequences ripple across cosmic time. Without this hierarchical growth, galaxies like ours wouldn't have the mass or structure to host stable solar systems, let alone life. Yet the Milky Way's appetite isn't sated. Right now, it's in the process of digesting the Sagittarius dwarf spheroidal, and in about 4 billion years, it'll collide with the Andromeda galaxy in a titanic merger that will reshape both into a single elliptical galaxy. These events aren't just historical footnotes, they're clues to the universe's grand narrative. By studying galactic mergers, astronomers piece together how structure emerges from chaos, how black holes and stars co-evolve, and ultimately how galaxies like ours came to be. Every stream of stars, every twisted orbit, is a sentence in the Milky Way's autobiography, written in the language of gravity, and the story is far from over. The Kuiper Belt should be a bustling cosmic highway filled with icy leftovers from the solar system's birth. But venture beyond Neptune, out around 50 astronomical units from the Sun, and something bizarre happens. The belt suddenly ends. It's not a gradual thinning like traffic fading at the edge of a city. It's a hard stop, a cliff edge where the number of objects drops off a statistical cliff. This boundary, known as the Kuiper Cliff, is one of the solar system's most jarring mysteries. If our models of planetary formation are correct, there should be thousands more objects out there, drifting lazily in the cold dark. So where did they all go? One explanation points to the gravitational hand of an unseen giant. Could a hidden planet lurking far beyond Neptune be clearing out the neighborhood? The hypothetical planet 9, thought to be 5 to 10 times Earth's mass, is a prime suspect. Its sheer gravity might have shepherded objects into odd, clustered orbits, or flung them into the abyss entirely. The math is compelling. Simulations show a distant super-Earth could sculpt the Kuiper Belt's sharp edge, leaving behind only the most resilient objects. But after years of searching, no telescope has spotted this phantom world, leaving astronomers to wonder if it's a cosmic ghost or just hiding too well. Then there's the wild card, planetary migration. In the solar system's chaotic youth, Jupiter and Saturn likely ricocheted inward and outward, their gravity scattering debris like a game of pinball. Some researchers suggest Neptune's outward march could have emptied the outer Kuiper Belt, dragging smaller objects along or ejecting them entirely. Others propose the cliff marks the outer edge of the primordial disk where the sun's material simply ran out, like a construction site where the builders didn't bring enough bricks. But the plot thickens when you consider the survivors. The few objects found beyond the cliff, like the dwarf planet Sedna, orbit in strange, elongated paths that defy easy explanation. Sedna never comes closer than 76 astronomical units, yet swings out as far as 930. A passing star could have yanked it into this odd orbit billions of years ago. Or perhaps it's another clue pointing to Planet 9's influence. The Kuiper Cliff isn't just a curiosity, it's a challenge to our origin story. Every missing object, every skewed orbit, is a question mark scribbled across the blueprint of the solar system. Upcoming telescopes like the Vera-Rubin Observatory might finally spot the culprit, whether it's a stealthy planet or traces of ancient upheaval. Until then, this empty edge stands as a silent reminder. Even in our own cosmic backyard, the universe keeps its secrets close. Neutrinos are the ultimate cosmic ghosts, particles so elusive they can pass through a light year of lead without slowing down. For decades, physicists assumed these tiny wanderers were massless, zipping through the universe at the speed of light like silent shadows. Then came the bombshell. Neutrinos change identities mid-flight, morphing between three distinct flavors: electron, muon, and tau as they travel. This chameleon-like trick, called neutrino oscillation, proved they must have mass. Not much. A single neutrino weighs 1,000,000 times less than an electron, but enough to crack open one of physics' most stubborn puzzles. Why does anything have mass at all? The implications are staggering. In the Standard Model, the rulebook for particle physics, neutrinos were never supposed to have mass. Their sudden refusal to play by the rules hints at gaps in our understanding, gaps that might hide entirely new physics. One leading theory points to the seesaw mechanism. If heavy, undiscovered neutrinos exist, their extreme mass could balance the feather-light neutrinos we observe, like a cosmic teeter-totter. These hypothetical particles, predicted by grand unified theories, could help explain why the universe is made of matter rather than antimatter. Here's how. In the early cosmos, heavy neutrinos might have decayed unevenly, producing slightly more matter than antimatter, a tiny bias that eventually gave rise to everything we see today. Then there's the eerie possibility that neutrinos are their own antiparticles, a property known as Majorana mass. If true, it would mean every neutrino could annihilate itself, a phenomenon that might explain dark matter or even power futuristic technologies. Experiments like Quor and Legend hunt for this by searching for neutrinoless double beta decay, a rare nuclear process that would vanish without a trace if neutrinos are Majorana particles. Yet the mystery deepens when you ask why neutrinos are so absurdly light. Their masses are billions of times smaller than the next lightest particle, as if nature hit the brakes on their heft for reasons we can't fathom. Some theories invoke extra dimensions where neutrino mass leaks into hidden realms. Others suggest spacetime itself has a graininess at microscopic scales, filtering neutrinos' interactions in ways that suppress their mass. The quest to weigh these phantoms is reshaping physics. Underground detectors like Supervoid and an ice cube watch for the faint flashes when neutrinos collide with atoms, while particle smashers search for hints of their heavy cousins. Every flicker of data carries the potential to rewrite the Standard Model, revealing forces or symmetries we've never imagined. Neutrinos aren't just cosmic afterthoughts, they might be the key to unlocking the universe's deepest secrets, from why we exist to what lies beyond the edge of physics itself. The Eridanus supervoid isn't just an empty patch of space. It's a cosmic anomaly so vast that light takes hundreds of millions of years to cross it. Stretching over 1.8 billion light-years, this staggering void is one of the largest structures ever discovered, a bubble of near-nothingness where galaxies are eerily sparse. But its true strangeness lies in what it's done to the oldest light in the universe, the cosmic microwave background. Embedded in that primordial glow is a mysterious cold spot, a chill in the cosmic radiation that aligns almost perfectly with the void's location. The odds of this happening by chance, astronomers estimate less than 1 in 50. So what's really going on here? One explanation leans on the physics of voids. When light enters these underdense regions, it loses energy climbing out of their shallow gravitational wells, an effect called the integrated Sachs-Wolfe effect. The result, the light redshifts slightly, leaving a cooler imprint on the CMB. But here's the catch. The Eridanus supervoid is so enormous that it shouldn't exist under standard cosmology. Inflation, the universe's explosive early growth, should have smoothed out such extreme density variations. The void's sheer size and its cold spot's intensity push our models to the breaking point. That's where things get speculative. Some theorists propose the void is a bruise, a relic of a collision with another universe in the multiverse. If our cosmos bumped against a neighboring bubble during inflation, the energy released might have carved out this colossal emptiness, leaving the cold spot as a cosmic fingerprint. It's a radical idea, but not impossible. Certain multiverse theories predict such collisions could create textures in space-time, regions where the fabric of reality is fundamentally twisted. Yet skepticism abounds. Critics argue the supervoid's galaxy count might not be low enough to explain the cold spot severity, suggesting the alignment could still be a fluke. Others wonder if we're misreading the data entirely. What if the cold spot isn't caused by the void but by something else entirely, an exotic form of dark energy? A flaw in how we measure cosmic distances. The debate rages because the stakes are so high. If the void is special, it could force a rewrite of inflation theory or even bolster the case for a multiverse. For now, the Eridanus supervoid remains a tantalizing riddle. Telescopes like the Dark Energy Survey and upcoming SIMBI experiments will scrutinize it further, hunting for clues in its ghostly contours. Whether it's a statistical oddity or a window into realities beyond our own, one thing's clear: the universe loves to defy expectations, and its emptiest places might hold the most surprising secrets. Empty space is anything but empty. At the quantum level, the vacuum of space boils with a strange, restless energy, a sea of virtual particles blinking in and out of existence so fast they defy detection. One moment there's nothing, the next an electron and its antimatter twin, a positron, flicker into being before annihilating each other almost instantly. This frenzied dance, known as quantum vacuum fluctuations, isn't just theoretical. It's been measured in labs through phenomena like the Casimir effect, where two uncharged metal plates placed micrometers apart in a vacuum are inexplicably pushed together. Why? Because the space between them restricts the wavelengths of virtual particles, creating a pressure imbalance that drives the plates to collide. But here's where the mystery deepens. If empty space crackles with this zero-point energy, why doesn't it manifest in ways we can easily observe? Calculations suggest the vacuum's energy density should be astronomically high enough to rip spacetime apart. Yet when we measure the cosmological constant, which describes dark energy's repulsive force accelerating the universe's expansion, the value is staggeringly small. This discrepancy, called the vacuum catastrophe, is one of the widest gulfs between theory and observation in all of physics. Some researchers propose that undiscovered symmetries or cancellation mechanisms might be at work, silently neutralizing most of this energy. Others wonder if dark energy itself is a manifestation of these fluctuations, a shadowy echo of the quantum foam shaping the cosmos on the grandest scales. The audacious dream of harnessing zero-point energy only adds to the intrigue. Imagine tapping into the universe's baseline energy, extracting power from pure nothingness. Science fiction loves the idea, but reality is far thornier. The energy tied to these fleeting particles is locked in a way that defies conventional extraction, like trying to catch smoke with your hands. Even if we could, the ethical and existential questions loom large. Would manipulating the vacuum's energy destabilize spacetime itself? Could it trigger unforeseen consequences, like decaying our current vacuum state into a lower energy one? A catastrophic event known as vacuum decay that would rewrite the laws of physics in its wake. For now, quantum vacuum fluctuations remain one of nature's most tantalizing puzzles. They blur the line between something and nothing, challenge our understanding of energy and gravity, and might even hold clues to the universe's ultimate fate. Every experiment probing their effects, from ultra-precise atomic clocks to gravitational wave detectors, brings us closer to answers, or perhaps to even bigger questions. One thing's certain: the emptiest places in the universe are far more alive than they appear. High above Earth, hidden in the glare of the sun or the shadow of the moon, conspiracy theorists insist something artificial and ancient silently circles our planet, the so-called Black Knight satellite. Stories claim it's been orbiting for 13,000 years, an alien sentinel left behind by some advanced civilization to observe humanity's rise. The tale is gripping, packed with grainy NASA photos and whispers of radio signals intercepted in the 1920s, but peel back the layers and the truth is far less cinematic. Most documented sightings trace back to mundane origins: a discarded thermal blanket from a spacewalk, a rogue piece of debris from a satellite launch, or even misinterpreted images from early space missions. So why does this myth cling with such tenacity? The answer lies in our primal fascination with the idea of cosmic surveillance. From ancient gods watching from the heavens to modern UFO lore, humanity has always projected its fears and curiosities onto the stars. The Black Knight myth taps into this deep-seated trope: the silent observer, the unknown intelligence cataloging our progress. It's no accident that the legend gained traction during the Cold War, a time of spy satellites and geopolitical paranoia. When what we know is being watched, it's a short leap to imagining what we don't know might be watching too. The myth's endurance also highlights how easily space exploration blurs fact and fiction. Astronauts have reported odd objects during missions: tools drifting away, ice crystals catching sunlight, but in the vacuum of space, even mundane phenomena can seem alien without context. The infamous Black Knight photo from the 1990s, often cited as proof, was later confirmed to show a thermal blanket lost during an STS-88 mission. Yet, like a cosmic Rorschach test, our brains fill in the gaps with narratives that feel more satisfying than orbital debris. Perhaps the most telling clue lies in the stories we ignore. Space is littered with artifacts of human activity: defunct satellites, spent rocket stages, even a Tesla Roadster drifting beyond Mars. These real objects lack the mystique of an ancient alien probe, so they fade into the background. The Black Knight persists precisely because it resists explanation, because it lives in the liminal space between our achievements and our imagination. It's a modern myth for the space age, a reminder that the unknown will always beckon, no matter how many telescopes we train on the sky. And in that sense, it serves a purpose far greater than any piece of floating debris. It keeps us looking up, wondering. Gravity might feel immediate. When you drop a cup, it shatters without delay. But how fast does gravity itself actually travel? According to Einstein's general relativity, gravity isn't a force acting at a distance. It's the bending of space-time, and any changes in that curvature ripple outward at the speed of light. If the sun vanished this instant, Earth wouldn't fly off into the void for another 8 minutes, the same time it takes sunlight to reach us. But proving this isn't as simple as watching a hypothetical cosmic disappearance act. The smoking gun came in 2017, when astronomers witnessed a collision of two neutron stars over 100 million light-years away. The event, dubbed GW170817, wasn't just seen, it was heard. Gravitational wave detectors LIGO and Virgo caught the spacetime ripples, while telescopes across the globe spotted the accompanying flash of gamma rays and light. The kicker: both signals arrived within 2 seconds of each other after traveling over 100 million years. If gravity moved at anything but light speed, the delay would have been far more pronounced. Einstein yet again seemed to have called it, but the story isn't quite that tidy. Some alternative theories of gravity, like massive gravity or certain quantum loop models, suggest subtle deviations. What if gravitational waves disperse slightly at different frequencies, like light through a prism? or if gravity's speed varies across extreme environments, near black holes or in the early universe's seething plasma. Even a tiny discrepancy could hint at new physics, revealing cracks in relativity's otherwise pristine facade. The implications stretch beyond theoretical curiosity. If gravity propagated instantaneously, black hole mergers would broadcast their gravitational ripples faster than their light appending causality itself. Wormholes, if they exist, might rely on gravitational anomalies to stay stable, and dark energy's accelerating push on the cosmos could trace back to how gravity interacts with spacetime's expanding fabric. Every fraction of a second in those neutron star detections isn't just data. It's a clue to the universe's deepest operating manual. The hunt for gravity's true speed is far from over. Next-generation detectors, like the space-based LISA mission, will listen for lower frequency waves from supermassive black holes where subtle speed variations could emerge. Others propose experiments with orbiting atomic clocks, measuring how Earth's gravity tweaks their ticks as the planet moves. Each test tightens the noose around the remaining unknowns. One thing's certain: whether gravity strictly obeys light speed or hides ghostly exceptions, the answer will reshape our understanding of everything from the birth of galaxies to the fate of spacetime itself. The Moon today is a silent, airless world, its surface scarred by ancient impacts and bathed in relentless sunlight or freezing shadow. But hidden within the lunar rocks brought back by Apollo astronauts lies a startling secret: traces of an ancient magnetic field. This discovery upends everything we thought we knew about how planetary magnetism works. Earth's magnetic field is generated by the churning of its molten iron core, a self-sustaining dynamo that requires massive size and heat to keep running. Yet the Moon, with just 1% of Earth's mass, somehow produced its own magnetic shield, one that may have rivaled Earth's in strength over 3 billion years ago. How and why did it vanish? One leading theory points to a lunar core that was once molten and turbulent, stirred by the colossal energy of the Moon's violent birth. The prevailing hypothesis suggests the Moon formed from debris ejected when a Mars-sized body, dubbed Theia, slammed into the early Earth. That cataclysm would have left the infant Moon seething with heat, its core liquid and electrically conductive. As it cooled, convection currents driven by the core's rotation and residual heat could have generated a magnetic dynamo, much like Earth's. But here's the catch: the Moon's core is tiny, about 500 kilometers across, and simulations show it should have cooled and solidified within a few 100 million years, far too soon to explain the magnetism preserved in those ancient rocks. Another possibility involves a dramatic cosmic assist. During the Moon's youth, Earth was much closer, its gravity tugging fiercely on the lunar interior. This tidal flexing could have kept the core molten longer, churning it like kneading dough. Some models even suggest Earth's gravitational pull might have spun the Moon's core faster, supercharging the dynamo effect. But again, the numbers don't quite add up. Tidal heating alone struggles to account for the field's surprising strength. Then there's the wild card: colossal impacts. The Moon's surface bears witness to a battering so intense it reshaped entire regions. When asteroid-sized objects slammed into the lunar crust, they might have triggered massive mantle movements, jolting the core like a spoon stirring a cup of coffee. These planetary-scale tremors could have briefly reignited the dynamo, creating intermittent bursts of magnetism recorded in the rocks. Yet this, too, is speculative. No impact we've modeled produces the sustained fields the data imply. The stakes go far beyond lunar geology. If small, rocky bodies like the Moon can generate strong magnetic fields, it reshapes our search for habitable worlds. Magnetic shields deflect deadly cosmic rays and solar winds, preserving atmospheres and, potentially, the delicate chemistry of life. Exoplanets once dismissed as too small might now be candidates for harboring protective fields of their own. The Moon's magnetic past also offers a time capsule of the early solar system, when planetary dynamos were the rule rather than the exception. Today, the Moon's core is a quiet relic, its magnetism long faded. But the mystery lingers, etched into those precious Apollo samples. Solving it might require drilling deeper into the lunar crust or deploying seismometers to map the core's remnants. Until then, the Moon stands as a cosmic riddle, proof that even the familiar worlds in our celestial backyard hold stories we're only beginning to read. The Sun's surface roasts at a blistering 10,000 degrees Fahrenheit, hot enough to vaporize steel. But step just above that searing boundary into the wispy outer atmosphere called the corona, and temperatures soar to millions of degrees. It's like walking away from a campfire only to be engulfed by an invisible inferno 10 times hotter. This cosmic contradiction, known as the coronal heating problem, has stumped solar physicists for decades. How can the Sun's atmosphere, farther from its nuclear furnace than we are from Earth's core, become so unimaginably hot? One leading suspect is magnetic reconnection, a process where the Sun's tangled magnetic field lines snap and realign like overstretched rubber bands, releasing explosive energy. Picture two trains barreling toward each other on the same track. When they collide, the wreckage isn't just metal, it's a fireball of kinetic energy converted to heat. On the Sun, this plays out in loops of plasma, where snapping magnetic fields hurl particles to relativistic speeds, superheating the corona. Satellites like NASA's Solar Dynamics Observatory have caught these reconnection events in action, but here's the catch. The energy they release seems too sporadic to explain the corona's constant extreme heat. Then there's the nanoflare theory. Instead of rare, colossal explosions, the corona might be heated by countless tiny flares, each no bigger than a millionth of a typical solar flare, but together a relentless hailstorm of energy. Think of it like popcorn. A single kernel popping barely warms your hand, but a microwave full creates a cloud of heat. The challenge: these nanoflares are too small and frequent for current telescopes to spot directly. We see their fingerprints, coronal loops glowing in ultraviolet, but proving they're the primary heat source remains elusive. Wave heating offers another tantalizing clue. The Sun's surface churns like a boiling ocean, generating seismic waves that ripple upward. Some researchers argue these waves, particularly a type called Alfvén waves, could carry energy into the corona, where friction or magnetic resonance dissipates it as heat. It's the astrophysical equivalent of rubbing your hands together to warm them, except on a scale where the hands are plasma filaments stretching taller than Earth. Recent observations by the Parker Solar Probe, which flew closer to the Sun than any spacecraft before, found evidence of these waves, but their energy contribution is still under fierce debate. The stakes stretch far beyond solar physics. Cracking the coronal heating mystery could revolutionize space weather forecasting. The corona's heat drives the solar wind, a stream of charged particles that, when it hits Earth's magnetic field, can knock out satellites, disrupt power grids, or dazzle us with auroras. Understanding how the corona stores and releases energy might let us predict these storms with life-saving precision. Even more tantalizing is the link to fusion energy. If we can decipher how the Sun's magnetic fields confine and heat plasma so efficiently, it could unlock breakthroughs in our own quest for clean, limitless power. For now, the corona remains a paradox, a place where the rules of heat and energy seem rewritten by forces we're only beginning to grasp. Every solar mission, every new algorithm analyzing magnetic fields brings us closer to an answer. Until then, the Sun's hidden furnace burns on, challenging us to rethink the very nature of heat in the cosmos. We know the universe is made of matter, protons, neutrons, and electrons combining to form everything from stars to smartphones. But when cosmologists tally up all the ordinary matter, or baryons, predicted by the Big Bang's nuclear recipes, they hit a glaring problem: nearly half of it is missing. Not dark matter, not some exotic particle, just the good old protons and neutrons that should be out there, plain as day. So where did it all go? The leading suspect is hiding in plain sight, woven through the vast cosmic web in threads of million-degree gas so faint we've barely begun to map them. This isn't just a bookkeeping error. The missing baryon problem strikes at the heart of our understanding of cosmic structure. According to meticulous calculations of the early universe's deuterium and helium abundances, baryons should account for about 5% of the universe's total mass energy. Yet when we count up all the visible stars, galaxies, and cold gas clouds, we're left with barely half that amount. For decades, astronomers assumed the rest must be lurking in diffuse reservoirs between galaxies' regions too dim to spot with conventional telescopes. Enter the warm-hot intergalactic medium, or WIM, a seething, ionized fog of gas stretching along the universe's filamentary scaffolding, where galaxies cluster like dew on a spiderweb. Detecting the WIM is like trying to photograph steam with a flashlight. Its gas is so hot it glows faintly in X-rays, but so thinly spread that its signal drowns in cosmic noise. The trick lies in catching its shadow. When light from distant quasars passes through these filaments, certain wavelengths get absorbed by oxygen and other heavy elements, chemical fingerprints of the WIM presence. It's akin to spotting a whisper-thin fog by the way it dims a faraway street lamp. The Hubble Space Telescope's Cosmic Origins spectrograph has bagged a few of these absorption lines, revealing tendrils of gas with temperatures between 10,000 and 10 million degrees. Still, these detections account for only a fraction of the missing matter. The real breakthrough might come from stacking data, combining thousands of quasar spectra to amplify the WIM faint signal from the noise. Meanwhile, X-ray observatories like ESA's Athena mission, set to launch in the 2030s, will scan the sky for the WIM thermal glow. Simulations suggest the gas isn't smoothly distributed. Instead, it clumps in knots and sheets around cosmic voids, stirred by galactic winds and supercluster collisions. If we can trace these structures, we'll finally close the gap in the baryon budget, but the implications go beyond ledger balancing. The WIM isn't just hiding matter, it's the universe's recycling plant. When galaxies collide or stars explode, they eject heavy elements into these filaments, seeding future generations of stars. The missing baryons might also solve a lingering puzzle: why some galaxies seem to have fewer heavy elements than expected. If the WIM hoards a significant portion, it could explain the discrepancy. The hunt for these phantom baryons is more than a cosmic scavenger hunt. It's a test of whether we truly understand the universe's anatomy, how it organizes its matter, fuels its galaxies, and evolves over eons. Every flicker of absorption, every wisp of X-ray glow brings us closer to an answer, and when we find it, we won't just solve a math problem, we'll uncover the hidden veins of the cosmos. Pulsars are cosmic wrecking balls, rapidly spinning neutron stars that form when massive stars collapse under their own gravity, exploding in supernovas so violent they can outshine entire galaxies. These remnants pack the mass of our Sun into a sphere smaller than Manhattan, spinning hundreds of times per second while blasting deadly radiation into space like a lighthouse from hell. Any planets foolish enough to linger nearby should have been vaporized by the blast or shredded by the pulsar's furious winds. Yet, against all odds, astronomers have found worlds not just surviving but thriving in these apocalyptic environments. The first confirmed pulsar planet, discovered in 1992 around PSRB 1257+12, defied every expectation. Here was a planet, possibly twice Earth's mass, circling a stellar corpse that had no business hosting anything at all. The mystery begins with the pulsar's birth. When a star goes supernova, the explosion unleashes enough energy to sterilize entire solar systems. The shockwaves alone should rip apart any pre-existing planets, scattering their debris into the void. So how did these worlds get there? One leading theory suggests they're second-generation planets born from the ashes of destruction. As the supernova's ejector cooled, a disk of metal-rich debris might have formed around the pulsar, condensing into new worlds like phoenixes rising from the inferno. These wouldn't be rocky planets like Earth, but bizarre, ultra-dense globes of crystallized carbon or even solid iron. Remnants of the dead star's core forged into something new. But survival is only half the battle. Pulsar planets face relentless bombardment. Their host stars emit jets of X-rays and gamma rays powerful enough to strip atmospheres and fry surfaces in seconds. Yet some, like the planets orbiting PSRB 1257+12, have endured for billions of years. How? One possibility is that they're shielded by unimaginably strong magnetic fields or cloaked in layers of degenerate matter, materials so densely packed they defy terrestrial physics. Others might be the scorched cores of gas giants, their outer layers blasted away, leaving behind a metallic heart stubbornly clinging to orbit. The most tantalizing question isn't just how these planets exist, it's whether they could harbor life. The odds seem laughably slim, but consider this: pulsars are incredibly stable timekeepers, their rotations precise enough to rival atomic clocks. If a planet orbited at just the right distance, it might bask in a narrow, habitable zone where the pulsar's heat, though faint, could sustain liquid water. The surface would be bathed in eerie, pulsing light, and any life would need to evolve under a sky crisscrossed by particle beams. It's a long shot, but nature has a habit of surprising us in the most hostile corners of the cosmos. Pulsar planets aren't just cosmic oddities, they're stress tests for our understanding of resilience. They force us to ask how far planet formation can stretch, what materials can endure extremes, and whether life's definition might be broader than we've dared to imagine. Every new detection pushes the boundaries of what's possible, reminding us that the universe doesn't play by our rules. Sometimes it rewrites them entirely. Imagine stepping outside on a clear night, gazing up at the cosmos, and instead of seeing a tapestry of stars against darkness, you're met with an unbroken wall of light, every inch of the sky glowing as brightly as the surface of the sun. That's the unsettling prediction of Olbers' paradox, a centuries-old riddle that asks, if the universe is infinite and filled with endless stars, why isn't the night sky blindingly bright? The answer, it turns out, isn't just about the stars themselves, but how the fabric of reality stretches and warps over cosmic time. Enter the Tolman effect, a modern twist on this paradox that reveals how the expanding universe plays tricks with light itself. At first glance, the logic seems airtight. In an infinite, static universe, every line of sight should eventually land on a star, no matter how distant. The night sky should be a searing expanse of light, like staring into a forest where the trees are so densely packed, you can't see the gaps between them. But the universe isn't static. It's stretching, carrying galaxies away from each other like dots on an inflating balloon. This expansion does something extraordinary to starlight. It stretches the wavelengths, shifting visible light into the infrared and beyond, a phenomenon we call redshift. The farther light travels, the more it's drained of energy, fading into obscurity before it ever reaches our eyes. Yet the Tolman effect takes this even deeper. Named after physicist Richard Tolman, it describes how the surface brightness of galaxies, their apparent glow per unit area, diminishes over cosmic distances, not just because of redshift, but because the light gets diluted across an expanding spacetime. Think of it like a flashlight beam spreading out in a foggy forest. The farther it travels, the dimmer and more diffuse it becomes. Tolman's equations show that in an expanding universe, even if the number of stars is infinite, their collective light never quite fills the sky. The night stays dark because the universe is fundamentally unequal. Today's stars shine brightly, but their ancient counterparts are stretched and smeared into near nothingness by the relentless march of cosmic time. But what if the universe weren't expanding? Here's where the paradox bites harder. Some alternative cosmologies, like the steady-state theory, propose that new matter continuously forms to fill the gaps left by expansion, keeping the universe's density constant. In such a model, Olber's paradox would resurface with a vengeance. The sky would glow unbearably bright because light from infinitely replenished stars would have no redshift to blunt its intensity. The darkness of our night sky, then, isn't just a quirk of astronomy. It's proof written in starlight that the universe had a beginning, that it evolves, and that the light we see is just a fleeting snapshot of a much grander, more dynamic story. The Tolman effect also hints at something even stranger, the limits of observation. Due to the universe's finite age and the speed of light, there's a horizon beyond which light hasn't had time to reach us. Beyond this cosmic event horizon, galaxies might as well not exist. Their light will never catch up to the expansion of space. This isn't just a theoretical boundary, it's a fundamental limit to what we can ever know. The darkness between the stars, then, isn't empty. It's a window into the universe's youth, a reminder that the cosmos isn't just out there. It's then and now, a living, breathing entity with a past we're still piecing together. So the next time you look up at the night sky and marvel at its depth, remember, the darkness isn't an absence, it's a signature, a cosmic fingerprint left by an expanding universe whispering secrets about time, light, and the very nature of existence. And in that quiet blackness, punctuated only by pinpricks of light, lies one of the most profound truths of all. The universe isn't just vast, it's alive, changing, and far stranger than we ever imagined. Galaxies aren't just colossal islands of stars, they're also threaded with invisible threads of magnetism, vast force fields stretching tens of thousands of light-years across space. Picture the Milky Way not merely as a swirling disk of dust and gas, but as a cosmic generator, its very motion weaving a tapestry of magnetic fields strong enough to steer charged particles and sculpt newborn stars. Yet here's the puzzle: these fields shouldn't exist, at least not in their current form. According to classic dynamo theory, the slow churn of galactic gas and stars should generate weak, disorganized magnetism, not the surprisingly strong, coherent fields we observe threading through spiral arms and halos like celestial railroad tracks. The mystery begins with the seed. Where do galactic magnetic fields even come from? One school of thought points to the early universe, where quantum fluctuations during inflation might have imprinted faint magnetic fields on primordial plasma. These primordial fields would have been laughably weak, billions of times fainter than a fridge magnet. But as galaxies formed, their rotation could have amplified these seeds through a process called the galactic dynamo. Imagine a bicycle dynamo scaled up to galactic proportions. Charged particles moving through existing magnetic fields generate electric currents, which in turn produce new magnetic fields, creating a self-reinforcing loop. Over billions of years, this cycle could theoretically amplify a whisper of magnetism into the roaring fields we detect today. But the dynamo theory hits a snag when confronted with young galaxies. Observations of distant, early galaxies, some just a billion years old, reveal magnetic fields already as strong as those in mature spirals like our own. There simply hasn't been enough time for a slow and steady dynamo to do its work. This has led to wilder ideas like turbulence from supernova explosions supercharging the dynamo, or cosmic rays high-energy particles zipping through galaxies, somehow injecting energy into the magnetic field. Others speculate that colossal galactic jets spewed by supermassive black holes might twist and amplify magnetism on unprecedented scales. Then there's the problem of coherence. Magnetic fields in galaxies aren't just strong, they're eerily organized, often aligning with spiral arms or forming huge, regular patterns. This is baffling because in most plasmas, magnetic field lines should tangle and dissipate like spaghetti in a blender. One possible explanation involves cosmic filaments, the universe's vast web of dark matter and gas acting as guides, channeling magnetic fields into orderly structures during galaxy formation. Alternatively, the fields might self-organize, with turbulence and rotation conspiring to comb the chaos into uniformity, like wind smoothing the surface of a lake. The stakes go far beyond academic curiosity. Galactic magnetic fields shape the life cycle of stars by regulating the collapse of gas clouds, deciding where and when new stars ignite. They also steer cosmic rays, high-energy particles that can influence planetary atmospheres and even biological evolution. Some researchers even suspect these fields play a role in the large-scale structure of the universe, guiding the flow of matter between galaxies. Yet for all their influence, galactic magnetism remains one of astrophysics' greatest blind spots. New telescopes like the Square Kilometre Array, with its unparalleled sensitivity to magnetic signatures, promise to map these invisible forces in unprecedented detail. Until then, we're left staring at the cosmic equivalent of a shadow puppet, show certain something vast is moving behind the curtain, but unsure of its true shape. What's clear is this: magnetic fields aren't just footnotes in a galaxy's story. They're hidden architects quietly shaping the universe from the shadows. And the deeper we look, the more we realize how much we've underestimated their silent, pervasive power. The universe's recipe book has a glaring typo, one that's been hiding in plain sight since the first minutes of creation. When protons and neutrons fused in the searing heat of the Big Bang, they cooked up precise amounts of helium, deuterium, and a tiny fraction of lithium-7. These predictions match observations almost perfectly except for that last ingredient. According to the math, there should be 3 to 4 times more lithium-7 floating around than we've ever detected. This cosmic accounting error, known as the lithium problem, isn't just a minor discrepancy, it's a crack in our understanding of the universe's earliest moments. So where did all the lithium go? One possibility is that our measurements are skewed. Most lithium abundance estimates come from ancient stars in the Milky Way's halo, relics from near the dawn of time. But stellar atmospheres are turbulent places, and lithium is fragile. It burns up at temperatures far cooler than stellar cores. Some researchers argue convection currents might drag lithium deep into these stars, effectively hiding it from our telescopes. Others suggest cosmic rays could be splitting lithium atoms apart in interstellar space before we get a chance to count them. Yet even after accounting for these factors, the gap persists, nudging scientists toward more radical explanations. What if undiscovered physics is at work? The early universe was a laboratory of extreme particle interactions, some of which might have left traces in elemental abundances. Hypothetical particles like actions or supersymmetric partners could have altered nuclear reaction rates, subtly suppressing lithium production. Another wild idea involves primordial black holes, tiny, dense objects peppering the cosmos that might have gobbled up lithium-rich regions before stars could form. Then there's the nuclear physics angle. Certain reaction cross-sections critical for predicting lithium yields might be miscalculated in our models. Experiments like Luna, which recreates Big Bang energies deep underground, are racing to check these numbers with unprecedented precision. The stakes here aren't just academic. Lithium is a key piece of the cosmic puzzle, a bridge between the universe's particle soup phase and the emergence of structure. If we're missing something fundamental about its creation or destruction, it could ripple through our understanding of everything from dark matter's influence on early chemistry to how the first stars enriched the cosmos with heavier elements. Future telescopes, like the Extremely Large Telescope, will probe lithium in even older stellar populations, while labs continue simulating the universe's first nuclear furnaces. Until then, the lithium problem stands as a quiet challenge, a whisper from the Big Bang that we're still learning how to hear. Every second, Earth is bombarded by cosmic rays, tiny particles zipping through space at nearly light speed. But a rare few defy all expectations, packing so much energy they make the Large Hadron Collider look like a toy. These ultra-high-energy cosmic rays exceed 10 to the power of 20 electron volts, carrying kinetic energy comparable to a baseball thrown at 60 miles per hour, all condensed into a single subatomic particle. The sheer violence of their origin scrambles the laws of physics as we know them, because particles this energetic shouldn't exist at all. According to a phenomenon called the Greisen-Zatseping-Kuzmin cutoff, cosmic rays from distant galaxies should hit a hard ceiling. As they travel, high-energy protons collide with photons from the cosmic microwave background, losing energy like a marathon runner trudging through molasses. Any particle over about 5 times 10 to the power of 19 electron volts should decay long before reaching Earth. Yet detectors like the Pierre Auger Observatory in Argentina keep catching these ultra-high energy outliers, defiant cosmic speedsters that shouldn't have lasted the journey. So what cosmic beasts are capable of such monstrous acceleration? Active galactic nuclei, supermassive black holes devouring whole stars, top the suspect list. Their accretion disks spin magnetic fields into cosmic slingshots, capable of flinging particles to unfathomable speeds. Some theories suggest turbulent shocks within these disks could act like natural particle colliders, stacking energy upon energy until protons become microscopic bullets. Even more extreme are blazars, galaxies whose black holes fire jets of plasma directly at Earth, turning them into celestial particle guns. Yet there's a catch. Many ultra-high-energy cosmic rays arrive from regions of space devoid of obvious powerhouses. That's led to wilder ideas like decaying super-heavy dark matter. Imagine a particle left over from the Big Bang, weighing as much as a bacterium but smaller than an atom. If such a particle decayed today, it could unleash a cascade of high-energy debris, including the cosmic rays we detect. Or perhaps the culprits are cosmic strings, defects in spacetime from the universe's infancy, snapping like rubber bands and releasing unimaginable bursts of energy. The real frustration lies in tracking them back to their source. Cosmic rays zigzag through interstellar magnetic fields, their paths as twisted as confetti in a storm. When a rare ultra-high-energy particle hits Earth's atmosphere, it triggers a shower of secondary particles, which detectors like Auger's sprawling array of water tanks can trace. But pinpointing the origin, that's like reconstructing a bullet's trajectory after it's ricocheted off a dozen walls. Solving this mystery could rewrite astrophysics. If black holes are the accelerators, their magnetic fields must be more efficient than any model predicts. If dark matter decays, it would signal a whole new class of particles beyond the standard model. And if the universe hides even more violent engines waiting to be discovered, our cosmic map just got a lot more interesting. For now, these particles remain cosmic enigmas, whispers of forces so extreme they stretch the limits of reality itself. The cosmic microwave background is often described as the universe's baby picture, a near-perfect snapshot of its infancy frozen in time. But zoom in closer, and there's a blemish on this otherwise smooth portrait. A vast, inexplicably cold patch spanning nearly 1 billion light-years, lurking in the constellation Eridanus. This so-called cold spot isn't just a minor irregularity, it's a blistering thorn in the side of modern cosmology, defying everything we thought we knew about the universe's birth. At first glance, the cold spot seems like it could be written off as a statistical fluke. After all, the CMB isn't perfectly uniform. It's speckled with tiny fluctuations, remnants of quantum ripples stretched across the cosmos by inflation. But the odds of a feature this extreme appearing by random chance, less than 1 in 50. When simulations of the universe's expansion fail to reproduce anything like it, scientists are forced to confront more radical possibilities. One leading theory suggests the cold spot might be a cosmic bruise, the imprint of a collision with another universe. In certain multiverse models, our cosmos isn't alone. It's one bubble among countless others in an eternally inflating sea. If another bubble brushed against ours during the Big Bang's afterglow, the energy released could have left behind a void, a pocket of distorted space-time where temperatures dipped anomalously low. It's a breathtaking idea, the cold spot as a literal fingerprint from beyond our cosmic horizon, a relic of an encounter with an alien reality. Then there's the texture hypothesis. Some exotic physics theories predict defects in spacetime itself, knots or tears that formed as the universe cooled, like cracks in freezing ice. These textures, if they exist, would warp the fabric of reality around them, subtly altering the CMB's temperature in their vicinity. The cold spot could be the shadow of one such structure, a fossilized tangle of spacetime from the universe's first seconds, but not all explanations require new physics. Could the cold spot be a supervoid, an underdense region of space so vast it stretches the limits of plausibility? As light traverses such voids, it loses energy climbing out of their weak gravitational wells, a phenomenon known as the integrated Sachs-Wolf effect. The problem: the largest known voids are still too small to explain the cold spot's intensity. For this to fit, we'd need a void of unprecedented scale, one that shouldn't exist under standard cosmology. The stakes here are immense. If the cold spot is a fluke, it's a reminder of how even our best models can be fooled by randomness. If it's evidence of new physics or a multiverse, it could force a rewrite of cosmology's foundational principles. Future telescopes like the Simons Observatory and CMB-S4 will scrutinize this anomaly with unprecedented precision, hunting for distortions in the CMB's polarization that might betray its true nature. For now, the cold spot remains a riddle written in the universe's oldest light, a whisper from the dawn of time that we're only beginning to decipher. Whether it's a cosmic scar, a statistical ghost, or something stranger still, one thing's certain: the universe loves to surprise us, and sometimes its coldest corners hold the most electrifying secrets. One of the most puzzling patterns in the hunt for alien worlds isn't what we've found, it's what's missing. When astronomers tally up the thousands of exoplanets discovered so far, a bizarre gap emerges. Planets between 1.5 and 2 times Earth's radius are vanishingly rare. It's as if the universe has a cosmic sieve, filtering out worlds in this specific size range while favoring those slightly smaller or larger. This curious void, dubbed the radius gap or Fulton gap after the researcher who first identified it, isn't just a statistical oddity. It's a window into the life and death struggles of planets where atmospheres are either ripped away or cling desperately to their rocky cores. The leading explanation for this gap revolves around a brutal stellar phenomenon called photoevaporation. Young stars, especially red dwarfs, are notorious for their violent tantrums, flares, and ultraviolet outbursts that can bombard nearby planets with enough energy to strip away their atmospheres over time. Imagine a planet roughly twice Earth size, large enough to accumulate a thick hydrogen envelope, but not massive enough to hold onto it under relentless stellar assault. As radiation blasts away its gassy shroud, the planet shrinks, crossing the radius gap until it's left as a bare, rocky core. Smaller planets with their weaker gravity might never accumulate much atmosphere to begin with, while larger ones have enough gravitational muscle to weather the storm. The gap, then, could be a graveyard of lost atmospheres, a fossil record of stellar violence written in planetary demographics. But photoevaporation isn't the only suspect. Another theory points to the planet's very origins. During formation, rocky cores embedded in protoplanetary disks might accrete thick atmospheres from surrounding gas until they hit a critical threshold where gravitational energy from incoming material heats the core, triggering runaway gas loss. This core-powered mass loss could create the same gap but through internal thermodynamics rather than external radiation. Picture a planet growing so hot from its own formation that it literally cooks off its atmosphere like a pot boiling over. The timing matters too. If this process happens early, before the star's radiation ramps up, it could leave behind a population of planets that never had a chance to grow into the missing sizes. Then there's the wild card, lava worlds. Some researchers suggest planets in the gap might not be missing at all, just disguised. A planet with 1.5 Earth radii could start as a rocky body with a thin atmosphere, but intense volcanic activity or a molten surface might outgas enough material to puff it up temporarily, bridging the gap before it settles back down. These worlds would be dynamic, chaotic places where the line between atmosphere and surface blurs, making them hard to categorize. The radius gap isn't just a quirk of planetary census data. It's a clue to one of the most fundamental questions in astrobiology: why some worlds become habitable Earth-likes while others wither into barren wastelands. If photoevaporation dominates, then stars with calmer radiation environments might host more planets snugly in the gap, potentially rich in retained atmospheres and oceans. If core-powered mass loss is the culprit, the gap could be a universal feature indifferent to stellar temperament. Future telescopes like the James Webb Space Telescope could settle the debate by analyzing the atmospheres of planets straddling the gap's edges, searching for signs of ongoing erosion or traces of ancient cataclysms. Every exoplanet census adds more pieces to this puzzle, sketching a portrait of planetary evolution that's far more dramatic than we ever imagined. The radius gap isn't empty, it's a story waiting to be read, one that reveals how the universe sculpts worlds, stripping some down to their bones while armoring others against the storm. And somewhere in that void lies the answer to why Earth, against the odds, ended up with an atmosphere worth holding onto. Quantum Darwinism is the universe's ultimate survival of the fittest, but instead of competing species, it's quantum states battling for existence in the arena of observation. At its core, this mind-bending theory asks why we don't witness the full chaos of quantum superposition in everyday life. Why don't chairs spontaneously split into multiple positions, or cats remain suspended between life and death? The answer might lie in an evolutionary process no one saw coming, the environment itself acting as a ruthless judge, selecting which quantum states get to stick around and which vanish into the void. Here's the paradox: quantum mechanics allows particles to exist in countless overlapping states until measured. Yet the macroscopic world feels solid, predictable, classical. Quantum Darwinism proposes that decoherence, the process where quantum systems interact with their surroundings, doesn't just erase superposition. It selects certain states based on their resilience. Imagine tossing a handful of glitter into a storm. Most flakes vanish instantly, but a few cling to surfaces, leaving behind a detectable pattern. Similarly, only quantum states robust enough to withstand constant environmental observation become part of our shared reality. This isn't conscious observation, but trillions of tiny interactions, air molecules, photons, even cosmic rays, that continuously measure the system, amplifying some states while suppressing others. The real twist: what we perceive as objective reality might just be the winning lottery numbers in a cosmic game of quantum chance. Take Schrödinger's famous cat. The moment the box interacts with the environment, say, a single photon bouncing off it, the superposition collapses into a state compatible with that interaction. Over countless such events, only the most stable outcome, a definitively alive or dead cat, survives the decoherence onslaught. This isn't magic, it's physics playing out like a high-stakes game of last man standing. Yet even this elegant framework leaves gaps. Why do certain states stabilize more easily than others? Why does the universe favor this version of reality over another? Some physicists argue quantum Darwinism doesn't fully explain the preferred basis problem, or why we perceive discrete objects in specific locations rather than smeared-out probability clouds. Others suggest it's part of a larger puzzle where entanglement and information play starring roles. What's clear is this: the theory bridges the schism between quantum weirdness and the tangible world, offering a map where before there was only mystery. Every time you see a chair sitting firmly on the ground, you're witnessing the aftermath of a silent quantum battle, one where the environment itself is both referee and executioner. And that's the most fascinating part. Reality as we know it might just be the last echo of a trillion quantum possibilities, filtered through the relentless sieve of existence. Galaxies aren't scattered randomly across the cosmos like leaves in the wind. They fall into distinct families, as neatly sorted as books on a library shelf. This cosmic filing system, known as the Hubble sequence, divides galaxies into elegant spirals, smooth ellipticals, and irregular oddballs. But how does the universe enforce this order? The answer lies in a delicate tug of war between gravity's relentless pull and the fiery chaos of star formation, all orchestrated on scales so vast they defy earthly intuition. Take spiral galaxies like our Milky Way. Their iconic arms aren't static structures but dynamic waves, cosmic traffic jams where gas and stars pile up like cars on a freeway. These patterns emerge from density waves, vibrations that ripple through a galaxy's disk, compressing gas and igniting star formation in their wake. Yet the arms themselves aren't permanent. Stars drift in and out over time, meaning the spiral we see is less a physical object and more a shimmering illusion, like a celestial Mexican wave. What keeps these patterns stable over billions of years? Dark matter likely plays a starring role, its invisible halo anchoring the galaxy's structure like a scaffold, while internal gas dynamics provide the fluidity needed to sustain the dance. Elliptical galaxies tell a darker story. These featureless orbs, devoid of spiral arms or gas-rich disks, are the cosmic equivalent of burned-out engines galaxies that exhausted their fuel or suffered violent mergers. When two spirals collide, their gas clouds slam together, triggering frenzied star formation until nothing remains but a sea of aging stars orbiting in chaotic paths. The result is a smooth, football-shaped swarm where random motions dominate. Unlike the orderly rotation of spirals, some ellipticals may have once been quasars, their cores glowing fiercely as supermassive black holes feasted on gas before blowing away the remnants in explosive winds. Yet the Hubble sequence isn't just about morphology, it's a timeline of galactic evolution. Spirals rich in gas are cosmic nurseries where new stars are born. Ellipticals, gas-poor and reddened by aging stars, represent retirement homes, and lurking between them are lenticular galaxies, the enigmatic hybrids that blur the line, like a spiral that lost its arms or an elliptical trying to remember its youth. The sequence may even reflect a galaxy's environment. Spirals thrive in isolated splendor, while ellipticals cluster in crowded galactic cities, their shapes sculpted by relentless collisions. But here's the puzzle that keeps astronomers up at night. Why don't we see more intermediate forms? If mergers gradually morph spirals into ellipticals, where are all the halfway galaxies? Some suggest the transition is abrupt, a single catastrophic merger, or a rapid burst of star formation that exhausts a galaxy's gas reserves in one go. Others point to supermassive black holes as cosmic regulators, their violent outburst shutting down star formation before a galaxy can settle into a hybrid state. The Hubble sequence isn't just a classification, it's a window into the universe's memory, a record of galactic births, deaths, and rebirths written in starlight. Every spiral's whirl, every elliptical's haze, whispers secrets about the forces that shape the cosmos, from the delicate ballet of gas clouds to the invisible hand of dark matter. And as we peer deeper into the night sky, we're not just cataloging galaxies, we're reading the universe's autobiography, one chapter at a time. Neutron stars are nature's ultimate pressure cookers, cosmic laboratories where matter gets squeezed beyond anything we can recreate on Earth. Picture the mass of our Sun crammed into a sphere smaller than Manhattan, creating densities so extreme that atomic nuclei cease to exist as discrete entities. At these pressures, electrons get crushed into protons, forging a sea of neutrons so densely packed they start behaving in ways that defy textbook physics. But here's the real question. What happens when you peer even deeper, past the neutron-rich crust and into the star's unfathomable core? The answer might rewrite our understanding of matter itself. One possibility is quark-gluon plasma, a primordial soup where individual neutrons dissolve into their fundamental building blocks. Under normal conditions, quarks are forever shackled together by the strong nuclear force, never roaming free. But in a neutron star's core, the pressure might be so intense that these bonds snap, liberating quarks to swirl in a seething, frictionless fluid. This state of matter hasn't existed naturally since the universe's first microseconds after the Big Bang. If it lurks inside neutron stars today, it would mean these cosmic remnants are time capsules, preserving conditions we've only glimpsed in fleeting particle collider experiments. Then there's the hyperon hypothesis. Hyperons are exotic particles that form when neutrons, under suffocating pressure, shed their identities entirely. Imagine a neutron so overwhelmed that it mutates, trading some of its quarks for strange quarks, a heavier, unstable variety that barely exists on Earth. The result, a core teeming with these ephemeral particles, constantly flickering in and out of existence like bubbles in boiling water. The catch, hyperon-rich matter, might be too soft to support the immense gravity of the heaviest neutron stars, leading to a paradox where theory clashes with observation. The wildest idea of all, absolute quark liberation. Some models suggest neutron star cores might harbor color superconductors, phases where quarks pair up and flow without resistance, mimicking the electron pairs in earthly superconductors but at energies a trillion times higher. These exotic states could generate bizarre magnetic fields or even crystalline structures, turning the core into a lattice of quark matter as dense as an atomic nucleus but spanning kilometers. Why does this matter beyond cosmic curiosity? Because neutron stars are the universe's most precise gravity probes. When two of them collide, the gravitational waves they emit carry fingerprints of their internal structure. A softer core rich in hyperons or free quarks would deform more easily during a collision, subtly altering the gravitational wave signal compared to a stiffer, conventional neutron core. Detectors like LIGO and Virgo are already hunting for these telltale distortions, which could reveal whether quark matter is fact or fiction. The deeper we dig into these mysteries, the clearer it becomes. Neutron stars aren't just dead suns. They're cosmic Rosetta Stones holding encrypted messages about the fundamental forces that shape reality. Every oscillation, every collision, every pulse of radiation is a clue waiting to be decoded. And tucked away in their crushing depths might be answers to questions we haven't even thought to ask. The Red Rectangle Nebula doesn't just defy expectations, it scoffs at them. While most planetary nebulae billow into delicate, asymmetrical clouds as dying stars shed their outer layers, this cosmic oddity presents itself with near-perfect geometric precision. Its sharp, crimson-tinged lines form an almost rectangular structure, crisscrossed by ladder-like rungs that give it the appearance of a celestial spiderweb. How could something so meticulously structured emerge from the chaotic death throes of a star? The answer might lie in the nebula's hidden heartbeat, a binary star system at its core, locked in a gravitational waltz so precise it sculpts chaos into order. At the heart of the Red Rectangle, a pair of aging stars dance in tight formation. their interactions channeling ejected gas and dust into bipolar jets, twin outflows fired perpendicular to their orbital plane. Unlike the ragged explosions of solitary stars, these jets are funneled with eerie symmetry, like water from a spinning garden sprinkler. Over time, the system's rotation and the star's mutual gravity have combed the expelled material into those unmistakable angular shapes. But there's another player in this cosmic origami: dust. The nebula's distinctive red hue comes from complex organic molecules called polycyclic aromatic hydrocarbons, which glow when bathed in ultraviolet light from the central stars. These carbon-rich compounds aren't just spectators, they might actively shape the nebula's structure, clotting into dense bands that further sharpen its edges. Then comes the magnetic wildcard. Some researchers speculate that magnetic fields, twisted by the binary star's motion, could act like invisible wires, guiding the outflowing gas into those stark, linear forms. Imagine a child swirling a magnet beneath a sheet of iron filings. The way the particles align into graceful arcs mirrors how magnetic fields might organize the red rectangle's geometry. Yet even this elegant idea runs into trouble when confronted with the nebula's finer details. Why are the rungs of its ladder so evenly spaced? Why does the structure remain so rigid over vast distances? Current models struggle to replicate such precision without invoking additional, unseen forces. The red rectangle isn't just a cosmic curiosity, it's a stress test for our understanding of stellar evolution. Most planetary nebulae are thought to blossom into butterfly or spiral shapes, their asymmetries reflecting the random turbulence of their birth. But this nebula's razor-straight lines suggest a level of control that challenges textbook theories. Is it a rare glimpse of how binary systems can impose order on stellar death? Or does it hint at entirely new physics governing gas dynamics in extreme environments? With the nebula's central stars destined to eventually collapse into white dwarfs, we're witnessing a fleeting masterpiece, a celestial artwork that refuses to fade into the background. Every observation peels back another layer, revealing not just how stars die, but how they can leave behind something inexplicably beautiful. Gravity waves ripple through our atmosphere like invisible ocean tides, shaping weather patterns in ways we're only beginning to decode. Unlike their cosmic counterparts, gravitational waves, which warp spacetime, these atmospheric waves are born from air itself. Colossal undulations triggered when stable air layers are jostled by mountains, thunderstorms, or even the sun's uneven heating. Picture a stone dropped into a pond. The initial splash disturbs the surface, sending concentric rings outward. Now imagine that stone is a towering mountain range, and the pond is an ocean of air stretching from the troposphere to the edge of space. That's the scale of these planetary scale oscillations, but here's where it gets fascinating. Gravity waves don't just fade into the background. They can travel thousands of miles, carrying energy and momentum from the Earth's surface to the upper atmosphere. When a gust of wind slams into the Andes or the Rockies, it doesn't just stop. It rebounds upward, creating waves that surge through the jet stream like a roller coaster. These waves eventually break, much like ocean waves collapsing on a shore, but their impact lingers. In the stratosphere, their energy dissipates as heat, influencing wind patterns and even nudging the polar vortex, that swirling behemoth of cold air that dictates winter extremes across continents. The real puzzle lies in their unpredictability. Some gravity waves amplify as they rise, while others fizzle out. Their behavior depends on factors as delicate as atmospheric stability, wind shear, and temperature gradients, variables so complex they've long been a blind spot in climate models. For decades, forecasters treated these waves as background noise, too chaotic to map, but satellite data has revealed their hidden order. Gravity waves often organize into coherent bands, crisscrossing the globe like the seams on a baseball. When these bands align just right, they can steer storms, intensify rainfall, or even trigger sudden stratospheric warming events, the atmospheric equivalent of a bomb going off. One of the most dramatic examples unfolded in 2018, when researchers traced a cascade of extreme winter weather across Europe and North America back to a single gravity wave eruption over the Tibetan Plateau. Like a domino effect in the sky, that initial disturbance disrupted the polar vortex, unleashing Arctic air deep into temperate latitudes. It's a stark reminder that the atmosphere operates as a connected system, where a ripple in one hemisphere can become a tidal wave in another. Yet modeling these waves remains a Herculean task. Current supercomputers struggle to simulate their fine-scale physics without sacrificing global coverage. The solution might lie in next-gen satellites like NASA's Atmospheric Waves Experiment, which will track gravity waves from the International Space Station with unprecedented resolution. By decoding their secrets, we could unlock more accurate long-range forecasts, better predict extreme weather, and even refine our understanding of how energy circulates between Earth's surface and space. The irony is poetic. These invisible waves, once dismissed as atmospheric static, might hold the key to forecasting the very storms they help create. Every mountain range, every thunderhead, every sunrise sends pulses through the sky, a silent symphony of motion that orchestrates the chaos of our weather. And as we learn to listen, the atmosphere's whispers are becoming a language we can finally begin to understand. Galaxies aren't supposed to exist without dark matter. It's like finding a car that runs without an engine. Yet nestled in the constellation Cetus, nearly 65 million light-years away, NGC 1052 DF2 defies every expectation. This ghostly, see-through galaxy, nearly the size of the Milky Way but with only 1% of its stars, presents astronomers with an unnerving reality. Its motions suggest almost no dark matter at all. When researchers first measured the velocities of its star clusters in 2018, the numbers came back shockingly low. Without the gravitational grip of dark matter's invisible scaffolding, those clusters should have flown apart long ago. The discovery sent ripples through astrophysics, challenging one of cosmology's bedrock principles that dark matter isn't just real, but essential to how galaxies form. So how did DF2 end up so empty? One possibility is cosmic robbery. Galaxies in crowded clusters often have their dark matter stripped away by gravitational tides, like a thief swiping the wheels off a parked car. DF2 lies near the massive elliptical galaxy NGC 1052, which could have plundered its dark matter during a close encounter billions of years ago. Yet simulations struggle to recreate this scenario without also disrupting DF2's delicate structure. Its stars remain oddly undisturbed, floating in a diffuse bubble that suggests a gentler origin. Then there's the more radical explanation. What if DF2 never had dark matter to begin with? Some theories propose it formed from gas expelled during a violent galactic collision, a process that might build galaxies without the usual dark matter seed. Imagine two galaxies crashing together, their collision flinging out a stream of gas that later condenses into stars. Without dark matter's gravitational primer, the resulting galaxy would look eerily like DF2, large, faint, and governed solely by the gravity of its visible stars. But here's the twist: DF2 isn't alone. A handful of other dark matter-deficient galaxies have since been spotted, including DF4, which seems to share DF2's bizarre properties. This raises an unsettling question. Could there be an entire population of galaxies that somehow bypassed dark matter's influence? If so, our models of galaxy formation might be missing a crucial chapter. The stakes couldn't be higher. If dark matter is as universal as we think, its absence in certain galaxies demands an explanation, one that either reveals new physics or forces us to reconsider how dark matter behaves in extreme environments. Future telescopes like the Vera Rubin Observatory will scan the skies for more of these outliers, testing whether DF2 is a cosmic fluke or the first clue to a hidden galactic diversity. Until then, it stands as a haunting reminder. The universe loves to break its own rules, and the most perplexing exceptions often lead to the greatest breakthroughs. Saturn's North Pole shouldn't look like this, not in a universe governed by fluid dynamics and chaos. Yet there it is, a perfect hexagon wider than two Earths, with razor-straight sides maintaining their geometric precision for at least 4 decades. This isn't some fleeting atmospheric quirk. It's a planetary-scale enigma, a 6-sided storm raging in slow motion while everything we know about gas giants says it should have dissolved into turbulence long ago. The hexagon's sheer persistence defies intuition. Jupiter's polar vortices twist and merge. Neptune's winds whip at supersonic speeds without settling into polygons. But Saturn's northern vortex locks into this impossible shape like a cosmic honeycomb, each of its 6 jet streams barreling forward at over 200 miles per hour while the corners hold firm. When the Cassini spacecraft first captured it in detail in 2006, scientists scrambled to explain how nature could produce something so eerily artificial-looking. Laboratory experiments offer tantalizing clues. Rotating fluids under controlled conditions can generate polygonal shapes, squares, triangles, even octagons when spun at just the right speeds. In one groundbreaking study, physicists filled a cylinder with water, set it spinning, then injected dye at the center. As the speed increased, the once circular flow morphed into a perfect hexagon, mimicking Saturn's pattern in miniature. The key seems to lie in sheer instability, where layers of fluid moving at different velocities create standing waves that lock into geometric forms. But scaling this up to a planet introduces staggering complexity. Saturn's atmosphere isn't a uniform fluid, it's a churning maelstrom of hydrogen, helium, and who knows what else, with depth-dependent densities and temperatures that could rewrite the rules. Some models suggest the hexagon might be a towering structure, extending hundreds of miles below the visible cloud tops, anchored by deep-rooted circulations we can't yet observe. Others propose it's a surface phenomenon, sculpted by interactions between Saturn's ferocious winds and its own rotation. Then there's the wild card, the hexagon's eerie synchronization with Saturn's radio emissions. The storm rotates almost perfectly in sync with the planet's mysterious kilometric radiation, a rhythmic pulse that some researchers think originates from currents deep in Saturn's interior. Could the hexagon be a surface manifestation of some deeper planet-wide resonance, a visible echo of invisible processes churning far below? The hexagon's longevity adds another layer of mystery. Earth's hurricanes dissipate within weeks. Jupiter's great red spot, while centuries old, shrinks and surges unpredictably. Yet Saturn's hexagon persists with military precision, unfazed by seasonal changes as the planet tilts through its 30-year orbit. This stability hints at something fundamental, a self-reinforcing feedback loop between the atmosphere's motion and Saturn's internal dynamics that we've barely begun to decipher. What makes this puzzle so compelling isn't just the hexagon itself, but what it represents, a glaring exception to our models of planetary fluid behavior. Every new observation from Cassini's treasure trove of data peels back another layer, revealing intricate cloud patterns, secondary vortices dancing at the hexagon's corners, and bizarre microstorms threading its edges. These details aren't just curiosities, they're breadcrumbs leading toward a deeper understanding of how energy flows, organizes, and dissipates in alien atmospheres. Until we send another probe to Saturn's North Pole, the hexagon remains a celestial Rorschach test. Is it a standing wave, a resonant cavity, a cosmic accident, or a signpost pointing toward physics we haven't yet imagined? One thing's certain. In a universe that favors chaos, Saturn's geometric stubbornness is a masterpiece of order, one that challenges us to rethink what's possible when fluids, gravity, and time collide on a planetary scale. The Unruh effect is one of quantum physics' most mind-bending predictions, a reminder that reality itself might depend on who's looking and how they're moving. Imagine floating in what appears to be perfect emptiness, the vacuum of space utterly devoid of particles. Now, picture accelerating through that same void at breakneck speeds. Suddenly, your instruments light up with the glow of particles, real, measurable heat where there was nothing before. To an outside observer watching you from a steady, unaccelerated frame, nothing has changed. The vacuum remains empty. This isn't a glitch in measurement. It's a fundamental feature of quantum field theory, where acceleration literally conjures particles from the void. At its core, the Unruh effect hinges on a radical idea borrowed from relativity. Acceleration and gravity are two sides of the same coin. Just as Hawking radiation predicts that black holes emit particles due to their immense gravitational pull, the Unruh effect suggests that an accelerating observer will detect a thermal bath of particles, Unruh radiation, while someone moving at constant velocity sees nothing. The particles aren't illusions. They're as real as the warmth you feel from sunlight, but their existence depends entirely on your state of motion. It's as if the universe has a secret rulebook where empty space isn't empty at all. It's a seething quantum foam that only reveals itself under extreme conditions. The math behind this phenomenon is hauntingly elegant. Quantum fields fluctuate constantly, even in a vacuum, with particle-antiparticle pairs blinking in and out of existence. Normally, these fluctuations cancel each other out, leaving no trace, but acceleration disrupts this balance. As an observer accelerates, they effectively catch up to certain quantum fluctuations while leaving others behind, creating an apparent horizon, a boundary separating what they can and cannot observe. Beyond this horizon, the fluctuations appear frozen, like a car speeding away from a siren whose pitch drops to silence. The result: the observer perceives these trapped fluctuations as real particles with measurable energy, a thermal glow proportional to their acceleration. Yet for all its theoretical beauty, the Unruh effect remains tantalizingly out of reach in the lab. To detect even a faint whisper of Unruh radiation, an observer would need to accelerate at billions of times Earth's gravity, far beyond the capabilities of current particle colliders. Some proposals involve using ultra-intense lasers to mimic the necessary conditions, while others speculate that high-energy cosmic rays or even future warp drive experiments might provide indirect clues. The challenge isn't just technical, it's philosophical. If confirmed, the effect would blur the line between perception and reality, forcing us to confront whether particles are truly fundamental or mere artifacts of our motion through spacetime. What's at stake goes beyond academic curiosity. The Unruh effect is deeply entwined with Hawking radiation, black hole thermodynamics, and even the holographic principle, the idea that our three-dimensional universe might be encoded on a two-dimensional surface. If accelerating observers create particles from nothing, could the same mechanism explain why black holes evaporate? Could it hint at a deeper connection between quantum mechanics and gravity, the holy grail of modern physics? Every unanswered question about Unruh radiation is a thread tugging at the fabric of our understanding, pulling us toward a universe where motion, heat, and even existence itself are far stranger than they seem. For now, the Unruh effect remains a ghost in the equations, a prediction so audacious it challenges the limits of experimentation. But in that challenge lies its allure. Whether it's confirmed or overturned, the quest to test it will push technology to its limits, probe the nature of reality, and remind us that sometimes the emptiest places in the universe are the ones hiding the most extraordinary secrets. From dark matter to neutron starquakes, the universe is a vast puzzle box, and we've barely scratched the surface of its deepest riddles. These 45 mysteries aren't just gaps in our knowledge, they're invitations to rewrite the textbooks. Think about it. Every time we've unraveled one cosmic secret, like the true nature of pulsars or the accelerating expansion of space, it's led to even wilder questions we never thought to ask. The anomalies we're chasing today, ghostly particles that pass through walls, galaxies without dark matter, stars that vanish without a trace, aren't just curiosities. They're clues to forces and phenomena that could redefine the very fabric of reality. Take the enigma of fast radio bursts, these millisecond blasts of energy, some flaring from billions of light years away, could be the death throes of magnetars or the fallout of cosmic collisions. Or just maybe there's something far stranger, a cosmic SOS we haven't learned to decode. Then there's quantum entanglement, that eerie, spooky action at a distance that even Einstein couldn't stomach. It challenges our most basic notions of locality, suggesting the universe might be far more interconnected than we ever imagined. These aren't just academic debates. They're windows into a reality where the rules we take for granted, cause and effect, the speed of light, the independence of objects, might be mere approximations of a deeper truth. What makes these mysteries so exhilarating is their sheer unpredictability. A single observation like ʻOumuamua's odd acceleration or the cold spot in the cosmic microwave background could force us to rethink everything from particle physics to the multiverse. The history of science is littered with moments like this, anomalies dismissed as noise until they became revolutions. Dark energy was once a blip in supernova data. Neutrinos were hypothetical phantoms until they started flooding our detectors. Who's to say the next paradigm shift isn't hiding in plain sight, waiting for us to connect the dots? So here's the real question: where do we go from here? The tools we're building, next-gen telescopes like the Vera Rubin Observatory, quantum computers that simulate black holes, labs hunting for WIMP and actions, aren't just upgrades. They're keys to unlocking dimensions we can't yet perceive. And the best part, you don't need a PhD to be part of this adventure. Citizen scientists are classifying galaxies, parsing telescope data, even spotting anomalies professionals missed. The universe doesn't discriminate, it speaks to anyone willing to listen. As we wrap up this cosmic tour, remember, every mystery solved opens 10 new doors. Maybe you're captivated by the thought of white holes, the universe's hypothetical rewind buttons, or the chilling silence of the Fermi paradox. Whatever sparks your curiosity, that's where the next breakthrough might begin. Drop your favorite enigma in the comments, debate it, dissect it, dream about it, because the greatest lesson these 45 puzzles teach us isn't just how much we don't know. It's how thrilling it's going to be to find out. Hit subscribe and let's keep exploring together. The cosmos has plenty more surprises